Hey, welcome to The Night Scientist. I'm so happy you're here. There's something truly magical about taking a moment to step back from the chaos of our daily lives and diving into the gentle mysteries that surround us every single day. You know, we live in this incredible universe where the most extraordinary stories are happening right under our noses, yet we often rush past them without even noticing. Today, I want to invite you to slow down with me, to breathe deeply, and to embark on a journey that's both profoundly scientific and deeply personal. We're going to explore something so fundamental, so essential to your very existence, that you literally cannot live without it for even a few minutes. And yet, it's something that most of us take completely for granted. So get comfortable, maybe grab a warm cup of tea or coffee, and let's settle in together for what I promise will be a fascinating and peaceful exploration of the hidden world around us. Today, we're diving into the fascinating world of the story of heat, from the sun to your skin. Now, I know what you might be thinking. Heat? That seems simple enough. We feel it when we step outside on a summer day, when we hold a hot cup of coffee, or when we snuggle under a blanket on a cold winter evening. But what I want to share with you today is that the story of heat is actually one of the most remarkable tales in all of science. It's a story that begins in the nuclear furnace at the heart of our sun, travels across the vast emptiness of space, dances through our atmosphere, and finally, in the most intimate and personal way possible, touches your skin and becomes part of your own body's symphony of sensation and survival. This isn't just physics. This is poetry written in the language of the universe itself. Let's begin our story where all stories of heat must begin, in a place that's simultaneously the most familiar and the most alien location in our solar system. Every morning you see it rise over the horizon, casting its gentle light across the world and warming your face. But what you're witnessing is actually the end result of a process so violent, so intense, and so magnificent that it defies our everyday understanding of reality. Deep within the core of our sun, buried beneath layers upon layers of plasma so dense that a teaspoon would weigh as much as a car, something extraordinary is happening every single second of every single day. Picture, if you will, a furnace that burns not wood or gas, but the very fabric of matter itself. In the sun's core, the temperature reaches an almost incomprehensible 15 million degrees Celsius. To put that in perspective, that's nearly 3,000 times hotter than the melting point of steel. At these temperatures, matter doesn't behave like anything we're familiar with on Earth. Atoms are stripped of their electrons, existing as naked nuclei in a cosmic dance of unimaginable energy. But here's where the story becomes truly magical. Under these extreme conditions, something happens that seems to violate everything we think we know about how the world works. Hydrogen nuclei, the simplest and most abundant atoms in the universe, begin to do something that should be impossible. You see, atomic nuclei are positively charged, and as we all know from basic physics, like charges repel each other. It's like trying to push two magnets together with their positive ends facing each other. They should push apart with tremendous force. Yet in the heart of the sun, these hydrogen nuclei overcome this fundamental force of nature through sheer overwhelming pressure and temperature. When they crash into each other with enough energy, something beautiful happens. They fuse together, combining to create helium nuclei in a process we call nuclear fusion. And in that moment of fusion, something profound occurs. The mass of the resulting helium nucleus is slightly less than the mass of the original hydrogen nuclei that created it. This tiny difference in mass, following Einstein's famous equation E equals mc squared, becomes pure energy. Now, this might sound like a small thing, but remember that the speed of light squared is an enormous number. So even a tiny amount of missing mass becomes a tremendous amount of energy. Every second, our sun converts roughly 4 million tons of matter into pure energy through this process. 4 million tons every single second. It's a number so large that our minds struggle to truly comprehend it, but the result is something we can feel on our skin every time we step into sunlight. This energy doesn't immediately leap from the sun's core to warm your face on a summer morning. Instead, it begins an epic journey that can take anywhere from 10,000 to 100,000 years. The photons of light and heat created in the sun's core must fight their way through the dense layers of the sun itself, bouncing and ricocheting like pinballs in a cosmic arcade game, slowly making their way toward the surface. Imagine being a single particle of light, born in the nuclear fires of fusion, trying to make your way through layers of matter so dense that you can only travel a few centimeters before bumping into another particle and bouncing off in a random direction. You might travel toward the surface for a while, then get knocked back toward the core. You might spiral around in circles for decades before making any real progress outward. It's a journey of incredible patience, a slow dance through the stellar medium that speaks to the immense scale and complexity of our nearest star. But eventually, after this long and winding journey, our photon of heat energy reaches the sun's surface, a region we call the photosphere. Here, the temperature has cooled to a mere 5,500 degrees Celsius, still hot enough to vaporize any known material instantly, but cool enough that the photon can finally break free from the sun's gravitational embrace and begin its next phase of the journey. And now begins perhaps the most remarkable part of our story. Our photon of heat energy, born in nuclear fire and aged through millennia of stellar wandering, suddenly finds itself free in the vast emptiness of space. In an instant, it transitions from being trapped in the dense, chaotic environment of the sun to racing through the near-perfect vacuum of space at the ultimate cosmic speed limit, the speed of light. 300,000 kilometers per second. It's a speed so fast that it makes our earthly experiences of speed seem almost comically slow. If you could travel at the speed of a light, you could circle the Earth 7.5 times in a single second. You could reach the moon in just over a second. But even at this incredible speed, the journey from the sun to Earth takes our photon just over 8 minutes to complete. 8 minutes. That means that the warmth you feel on your skin right now actually left the sun 8 minutes ago. You're feeling the past in a very real sense. If the sun were to suddenly disappear, we wouldn't know it for 8 minutes. The heat and light we depend on for life itself is always carrying news from our recent cosmic past. But what's truly extraordinary about this journey through space is not just the speed, but the nature of the medium through which our photon travels. Space, as we often hear, is largely empty. But this emptiness is not the simple absence of matter that we might imagine. It's a dynamic, active emptiness, filled with invisible fields and forces that shape the very fabric of reality. Our photon travels through the solar wind, a stream of charged particles flowing outward from the sun at speeds of hundreds of kilometers per second. It passes through regions where magnetic fields twist and dance, where cosmic rays streak by at nearly the speed of light, where the very space itself is curved by the gravitational influence of massive objects. The emptiness of space is actually a rich tapestry of invisible phenomena, all of which our heat-carrying photon must navigate on its journey to Earth. As our photon races through this cosmic landscape, it carries with it not just energy, but information. The specific wavelength of the light tells a story about the conditions under which it was created. The polarization, the direction of its electromagnetic oscillations, carries clues about the magnetic fields it has encountered. In a very real sense, each photon is a messenger, carrying news from the sun about the state of our local stellar environment. And there are so many of these messengers. The sun emits roughly 10 to the 45th power photons every second. That's a number so large that if you tried to count them, with each count taking 1 second, you would need more time than the universe has existed to finish counting even 1 second's worth of solar photons. This incredible flood of energy streams outward in all directions, carrying with it the power that drives virtually every process on Earth. But our individual photon, the one whose story we're following, doesn't know about the trillions upon trillions of its companions. It travels alone through the darkness, a solitary messenger carrying its tiny packet of heat energy toward a small blue planet that awaits its arrival. After its 8-minute journey through the void, our photon finally encounters something substantial, the edge of Earth's atmosphere. This moment marks the beginning of perhaps the most complex and beautiful part of our heat story. What happens next is not a simple matter of the photon continuing its straight-line path to the surface. Instead, it enters into an intricate dance with the layers of gas that surround our planet, a dance that will determine not just whether the photon reaches the surface, but how it will be transformed along the way. Earth's atmosphere is far more complex than most of us realize. It's not just a uniform blanket of air, but a carefully layered system, each layer with its own temperature, pressure, and composition characteristics. Our photon first encounters the thermosphere, the outermost layer where the air is so thin that the few molecules present can be heated to temperatures over 1,000 degrees Celsius by solar radiation, yet you would freeze to death because there are so few molecules to transfer that heat to your body. As our photon descends through this tenuous layer, it begins to encounter more and more molecules. Each encounter is a chance meeting, a random collision between our messenger of heat and the atoms and molecules that make up our protective atmospheric blanket. Some of these encounters result in the photon being scattered, knocked slightly off course like a ball bouncing off a wall. Others result in the photon being absorbed entirely, its energy transferred to the molecules it encounters, causing them to vibrate more rapidly, to move with greater energy, to become, in essence, warmer. This process of scattering and absorption is what gives our sky its colours and our weather its energy. The blue light from the sun is scattered more than other colours by the small molecules in our atmosphere, which is why we see the sky as blue on a clear day. The red and orange light, including much of the infrared heat radiation, is scattered less and can penetrate more deeply into the atmosphere. Our photon, carrying its precious cargo of heat energy, continues its descent through the stratosphere, where it encounters ozone molecules that absorb much of the sun's ultraviolet radiation, protecting life on the surface from this harmful energy. This is one of the atmosphere's many protective functions, filtering out the types of solar radiation that would be dangerous to living organisms while allowing through the wavelengths that bring warmth and enable photosynthesis. In the troposphere, the lowest layer of the atmosphere and the one in which we live and breathe, our photon encounters water vapor, clouds, dust particles, and all the complex chemistry of weather systems. Here, the story becomes even more intricate. Water vapor in the atmosphere can absorb infrared radiation, the type of light that we experience as heat. Clouds can reflect sunlight back to space, or absorb and re-radiate it in different directions. Dust and pollution particles can scatter light, creating the hazy conditions we sometimes see on smoggy days. But let's imagine that our particular photon is fortunate. Let's say it encounters relatively clear skies, minimal cloud cover, and atmospheric conditions that allow it to continue its journey toward the surface with most of its energy intact. As it descends through the final kilometers of atmosphere, the air becomes denser and denser, but still our photon presses on, carrying its message of warmth from the nuclear fires of the sun. The atmosphere has done more than just filter and scatter our photon's energy. It has also created the conditions that make Earth a place where heat can be experienced as we know it. Without the atmosphere, our planet would be a lifeless rock with extreme temperature variations, blazing hot on the day side and frozen on the night side. The atmosphere moderates these extremes, creating the stable, temperate conditions that allow for liquid water, weather patterns, and ultimately life itself. And then, finally, after its epic journey from the sun's core through the depths of space and the layers of our atmosphere, our photon encounters something solid. Perhaps it strikes a leaf on a tree, or a patch of soil, or the concrete of a sidewalk, or maybe, just maybe, it makes contact with human skin. This moment of first contact represents a fundamental transformation in our story. The electromagnetic energy that has travelled so far for so long is about to become something entirely different. Heat as we experience it. When our photon strikes matter, several things can happen. It might be reflected, bouncing off the surface, and beginning a new journey in a different direction. It might pass through the material if it's transparent to that particular wavelength of light. But most likely, especially if we're talking about the infrared radiation that carries heat, our photon will be absorbed by the atoms and molecules in the material it strikes. This absorption is where the magic really happens. When a photon is absorbed by matter, its electromagnetic energy is converted into kinetic energy, the energy of motion. The atoms and molecules in the material begin to vibrate more rapidly to move with greater intensity. At the microscopic level, what we call heat is really just the rapid, chaotic motion of tiny particles. The faster they move, the hotter the material becomes. But this is only the beginning of the story of how solar energy becomes the heat you feel. The material that has absorbed our photon's energy doesn't just sit there, vibrating happily in isolation. Heat, once created, has a restless nature. It wants to move, to spread, to find equilibrium. And so begins the next phase of our journey, the process by which heat travels from the point where our photon was absorbed to eventually warm your skin and become part of your sensory experience. If our photon struck the ground, the heat it created might be conducted through the soil, warming the earth beneath your feet. It might rise through convection, heating the air around you and creating the gentle breezes that carry warmth to your body. If it struck a rock, that rock might become warm to the touch, ready to transfer its heat to your hand if you were to rest it on the stone surface. The Earth's surface is constantly receiving this bombardment of solar energy, billions upon billions of photons every second striking every square meter of our planet's surface. Some of this energy is reflected back to space, but much of it is absorbed, heating the land, the oceans, and the atmosphere. This absorbed solar energy drives our weather systems, powers the water cycle, enables photosynthesis in plants, and creates the thermal environment in which all life on Earth exists. But our story isn't just about physics and chemistry. It's also about the incredible complexity and beauty of how energy flows through natural systems. The heat from our single photon, once absorbed, becomes part of a vast interconnected web of energy transfer that includes everything from the slow warming of massive ocean currents to the rapid chemical reactions in a single cell. Consider for a moment the elegance of this system. Solar energy arrives at Earth as electromagnetic radiation, gets absorbed and converted to thermal energy, drives evaporation from the oceans to create water vapor, powers wind patterns that distribute heat around the globe, enables photosynthesis that captures carbon and releases oxygen, and ultimately creates the warm, oxygen-rich environment that allows complex life to flourish. Every breath you take, every step you walk, every thought you think is powered by this ancient nuclear energy that began its journey in the sun's core perhaps hundreds of thousands of years ago. Now that our photon's energy has been absorbed and converted into heat somewhere on Earth's surface, a new chapter of our story begins. Heat, as we're discovering, is not content to stay where it's created. It moves through the world around us in three fundamental ways, each with its own character and story to tell. Understanding these pathways of warmth is crucial to understanding how the solar energy we've been following eventually reaches your skin and becomes part of your personal experience of the world. The first pathway is conduction, perhaps the most direct and intimate form of heat transfer. Imagine the heat from our absorbed photon warming a metal handrail in the sunshine. The energy causes the atoms in the metal to vibrate more rapidly, but these atoms don't stay isolated in their excitement. They bump into their neighbours, sharing their kinetic energy, through direct contact. These neighbours then bump into their neighbours, and so on, creating a cascade of molecular motion that spreads heat through the material. This process happens relatively quickly in good conductors like metals, which is why a metal spoon left in a hot cup of coffee quickly becomes too hot to touch. The thermal energy races through the crystalline structure of the metal, carried by freely moving electrons that can transfer energy efficiently from atom to atom. But conduction also happens in other materials, just more slowly. Even through your clothing, through the wood of a park bench, through the stone of a warm wall, heat energy can travel by conduction, eventually reaching your skin if you make contact with these warmed surfaces. The second pathway is convection, a process that requires the movement of fluids, whether liquids or gases. When our photon's energy warms a patch of ground, that ground heats the air directly above it. Warm air is less dense than cool air, so it begins to rise, carrying its thermal energy upward like an invisible balloon. As this warm air rises, cooler air flows in to take its place, which then gets heated in turn and also begins to rise. This creates circulation patterns, currents of moving air that carry heat energy from place to place. You've experienced convection countless times without perhaps thinking about it. The warm air rising from sun-heated pavement on a hot day, the gentle breeze that carries warmth from a sunny spot to a shaded area, the circulation of air in a room warmed by sunlight streaming through a window. All of these are examples of convection distributing the heat energy that originally came from our sun through the movement of fluids.
Convection operates on scales both intimate and vast. In your cup of coffee, convection currents carry heat from the bottom of the cup to the top, keeping your drink uniformly warm. In the atmosphere, convection drives weather systems that can span continents, carrying heat from the equator toward the poles and creating the complex patterns of wind and weather that shape our climate. The third pathway is radiation, and this brings us full circle to where our story began. Any object that contains thermal energy radiates electromagnetic waves. The warmer the object, the more intensely it radiates, and the shorter the wavelengths it emits. This is how our photons' energy, once absorbed and converted to heat, can become new photons that carry that thermal energy through space without requiring any material medium. When you stand near a warm wall that has been heated by the sun, you can feel warmth on your skin even without touching the wall or without any air movement. This is radiant heat transfer. The wall is emitting infrared radiation, invisible to your eyes but detectable by the thermal sensors in your skin. In a very real sense, the wall is creating new photons of heat energy and beaming them directly to your body. These three pathways of heat transfer don't operate in isolation. In the real world, they work together in complex, beautiful ways. Sun-warmed rock conducts heat into its interior and surface, creates convection currents in the air around it, and radiates infrared energy to nearby objects. A warm breeze carries heat by convection, but that moving air also conducts heat when it comes into contact with your skin. And the warm air itself radiates infrared energy in all directions. This interplay of heat transfer mechanisms is what creates the rich thermal environment we live in. It's why you can feel warmth in so many different ways. Why the sensation of heat can be gentle and diffuse or sharp and direct. Why sometimes you feel warm even in cool air. And why sometimes you feel cool even when the air temperature is high. The thermal world around us is a symphony of energy in motion, and understanding its melodies helps us appreciate the elegant complexity of how solar energy eventually reaches our bodies. As our heat energy moves through the world via conduction, convection, and radiation, it encounters something truly remarkable: the living landscape. Life on Earth has evolved not just to tolerate the thermal energy that flows from the sun, but to harness it, channel it, and use it in ways that are both practical and beautiful. Every plant, every animal, every microorganism is part of a vast biological network that captures, transforms, and redistributes solar energy in forms that make complex life possible. Consider the leaf of a tree, perhaps the very leaf that our photon struck when it first made contact with Earth. This simple, green structure is actually one of the most sophisticated energy conversion devices in existence. Through the process of photosynthesis, it captures photons of light energy and uses them to power chemical reactions that combine carbon dioxide from the air with water from the soil to create glucose and oxygen. This process doesn't just store energy in chemical form. It also creates the oxygen-rich atmosphere that allows animals like us to exist. But photosynthesis also involves heat in important ways. The leaf absorbs not just visible light, but also infrared radiation, the form of electromagnetic energy we experience as heat. Some of this heat energy is used directly in the photosynthetic process, providing the activation energy needed for certain chemical reactions. Some is stored in the chemical bonds of the glucose molecules that are created, and some is released back into the environment through transpiration, the process by which plants release water vapor through their leaves. This transpiration is a beautiful example of how living systems manage heat. As water evaporates from the leaf's surface, it carries away thermal energy, cooling the plant just like perspiration cools your body. But this cooling effect doesn't just benefit the plant. The water vapor released into the atmosphere carries energy that can form clouds, influence weather patterns, and eventually return to Earth as precipitation that nourishes other living systems. Animals, too, have evolved sophisticated ways of managing thermal energy. Birds and mammals maintain constant body temperatures through metabolic processes that are ultimately powered by solar energy captured by plants and passed up through food chains. Reptiles bask in the sun to warm their bodies and seek shade to cool down, directly using solar radiation to regulate their body temperature. Even cold-blooded creatures like insects use behavioral strategies to optimize their thermal environment, positioning themselves to catch warming sunlight or seeking cool refuges when they need to avoid overheating. The soil beneath our feet is alive with thermal activity. Microorganisms in the soil use heat, energy to drive metabolic processes that break down organic matter and release nutrients that plants can use. Earthworms and other soil creatures move through temperature gradients in the earth, seeking optimal thermal conditions for their biological processes. The decomposition of organic matter generates heat, creating warm spots in compost piles and forest floors, where biological activity is particularly intense. Water systems, too, are shaped by the flow of thermal energy. Lakes and oceans absorb vast amounts of solar heat during the day and in summer, then release this heat gradually during the night and in winter, moderating temperature extremes and creating stable thermal environments for aquatic life. The thermal stratification of lakes, where warmer water floats on top of cooler water, creates distinct ecological zones that support different communities of organisms. But perhaps most remarkably, life has learned to create thermal environments that enhance its own survival. Forest canopies moderate ground temperatures, creating cooler, more stable conditions below. Coral reefs create complex three-dimensional structures that channel water flow and create thermal microclimates. Even bacterial mats in hot springs create layered communities where different species thrive at different temperatures within the same small area. All of this biological activity is connected by flows of energy that ultimately trace back to our sun. The glucose created by photosynthesis powers the growth of plants, which become food for herbivores, which become food for carnivores. The heat released by metabolic processes warms the bodies of living creatures and their immediate environments. The thermal regulation behaviors of animals create patterns of movement and activity that shape ecosystems and influence the distribution of species. In this living landscape, heat is not just a physical phenomenon but a biological necessity, a driver of evolution, and a connector that links all living things to the nuclear furnace at the heart of our solar system. Every time you see a bird spreading its wings to catch the morning sun, or a cat curling up in a warm patch of sunlight, or a flower turning to follow the sun's path across the sky, you're witnessing life's intimate relationship with the thermal energy that makes existence possible. Now our story takes us on perhaps the most remarkable journey imaginable. Picture, if you will, the moment when that precious bundle of energy we've been following breaks free from the sun's blazing surface. It begins what scientists call the most extraordinary voyage in our solar system, a journey through the vast, seemingly empty expanse we call space. But here's where our story becomes truly magical. This energy, this heat that will one day warm your skin, doesn't need anything to travel through. Unlike sound, which needs air to carry its vibrations, or a ship that needs water to sail upon, heat energy moves through space as electromagnetic radiation, requiring nothing at all to support its journey. It's as if our energy has learned to fly through pure nothingness, carrying within itself everything it needs to cross the cosmic void. Imagine standing on a beach at night, watching a lighthouse beam sweep across the darkness. That beam travels instantly across the water, needing no bridge, no path, no medium to carry it. This is how our heat energy moves through space as waves of light and radiation that dance through the emptiness at the most fundamental speed possible in our universe. The speed of light. At this incredible velocity of nearly 300 million meters per second, our energy begins its 8-minute and 20-second journey from the sun to Earth. Think about that for a moment. In the time it takes you to brew a cup of tea, heat generated in the sun's core has traveled 150 million kilometers to reach our planet. Every photon of sunlight touching your face right now began its journey in the sun's nuclear furnace just over 8 minutes ago. But our energy doesn't travel alone. It's part of an incredible symphony of electromagnetic radiation that pours continuously from the sun in all directions. Some of this energy vibrates as visible light, the warm yellows and brilliant whites we see when we look up at our star. Other portions vibrate as infrared radiation, the invisible heat waves that will eventually warm your skin. Still others oscillate as ultraviolet light, radio waves, and even tiny amounts of X-rays and gamma rays. Picture this river of energy as it flows outward from the sun like ripples on an infinite pond. The energy spreads in all directions, creating an enormous sphere of radiation that grows larger and larger as it moves away from its source. By the time this sphere reaches Earth's distance from the sun, it has expanded so much that our entire planet intercepts only about 1/2 billionth of the sun's total energy output. Yet even this tiny fraction is enough to power all life on Earth, drive our weather systems, and create the gentle warmth you feel on a sunny day. As our energy travels through space, it maintains its essential character while experiencing something quite beautiful. The vacuum of space is not the violent, chaotic environment you might imagine. Instead, it's remarkably peaceful, a realm of profound quiet where our energy can journey undisturbed. There are no air molecules to scatter the light, no dust particles to absorb the heat, no storms to battle through. Just pure, unfiltered cosmic silence through which waves of energy flow like gentle ripples on an invisible ocean. During this voyage, our energy encounters the occasional dust grain or gas molecule remnants from ancient stellar explosions, material slowly being expelled from the sun itself. But these encounters are so rare that they barely affect the energy's journey. It's like walking through a vast, almost empty cathedral where you might occasionally brush against a single dust mote floating in a shaft of sunlight. The energy that left the sun as part of a chaotic, violent fusion reaction now travels with perfect steadiness through space. Each photon, each tiny packet of energy maintains its specific wavelength and frequency, carrying within itself the signature of its nuclear birth. Some photons vibrate rapidly, carrying high energy as blue and ultraviolet light. Others oscillate more slowly, carrying their energy as red light and infrared heat. This diversity of wavelengths creates the full spectrum of solar radiation that will eventually reach Earth's atmosphere. As our energy approaches Earth after its 8-minute voyage, it encounters the first significant obstacle in its journey. Since leaving the sun, ahead lies our planet's atmosphere, delicate, layered blanket of gases that surrounds Earth like the most intricate protective shell imaginable. This atmospheric envelope, though it seems like nothing more than the air we breathe, will profoundly transform our energy's journey in ways both subtle and dramatic. The moment our solar energy encounters Earth's atmosphere marks the beginning of one of nature's most elegant and complex performances. Picture our planet wrapped in layers of air so thin that if Earth were an apple, the atmosphere would be no thicker than the apple's skin. Yet within this delicate envelope, our heat energy will undergo transformations that determine whether it reaches the surface as gentle warmth or gets redirected back into space. The atmosphere our energy encounters isn't a single, uniform blanket of air. Instead, it's a carefully layered system, each level with its own personality and role in the grand dance of energy transformation. At the very top, nearly 600 kilometers above Earth's surface, lies the exosphere, a realm so thin it barely qualifies as atmosphere at all. Here, individual molecules float in near-vacuum conditions, occasionally colliding like distant ships passing in cosmic fog. As our energy penetrates deeper, it encounters the thermosphere, where the few molecules present absorb the most energetic portions of solar radiation. The ultraviolet and X-ray components of our energy bundle, the most aggressive forms of solar radiation, meet their match here. These high-energy photons collide with oxygen and nitrogen molecules, breaking them apart and creating the ionosphere, a layer of electrically charged particles that protects us from the most harmful forms of solar radiation. It's here that something beautiful happens. As these energetic photons sacrifice themselves to protect life below, they create the shimmering curtains of aurora that dance across polar skies. The same energy that began in the sun's core now manifests as ethereal green and blue lights that ripple across the darkness like celestial silk scarves. Our energy has become part of one of nature's most magnificent light shows. But most of our energy, the visible light and infrared heat that will eventually warm your skin, continues its descent through increasingly dense layers of atmosphere. In the mesosphere, about 50 kilometers above the surface, the air becomes thick enough to burn up most meteors in brilliant streaks of light. This is where our energy begins to encounter more significant interactions with atmospheric gases. The real transformation begins as our energy enters the stratosphere, home to the ozone layer that sits like a protective umbrella between 15 and 35 kilometers above Earth's surface. Here, ozone molecules, each composed of 3 oxygen atoms linked in a unique molecular dance, absorb much of the ultraviolet radiation that would otherwise prove harmful to life below. This absorption process actually warms the stratosphere, creating a temperature inversion that helps stabilize this atmospheric layer. As our energy continues its descent, it encounters the most familiar part of Earth's atmosphere, the troposphere, where all weather occurs and where we live and breathe. This bottom layer, extending from Earth's surface to about 12 kilometers high, contains about 80% of the atmosphere's total mass. It's here that our energy will experience its most dramatic transformations before finally reaching the surface. Troposphere greets our incoming solar energy like a vast, ever-changing theater. Water vapor swirls in invisible currents, sometimes gathering into towering clouds that can redirect our energy in spectacular ways. Dust particles and microscopic droplets float suspended in the air, each one capable of scattering or absorbing portions of our energy bundle. The very molecules of nitrogen and oxygen that make up most of our atmosphere interact with our energy in subtle but important ways. One of the most beautiful aspects of this atmospheric dance is how different wavelengths of our energy are treated differently. Blue light, with its short wavelength and high energy, gets scattered more readily by air molecules in a process called Rayleigh scattering. This is why our sky appears blue and why sunsets paint the horizon in warm reds and oranges. The blue light has been scattered away, leaving the longer red and orange wavelengths to reach our eyes directly, the infrared heat portion of our energy. Warmth you'll eventually feel on your skin behaves differently. These longer wavelengths interact less with air molecules, but are readily absorbed and re-emitted by water vapor and carbon dioxide in the atmosphere. This creates the natural greenhouse effect that keeps our planet warm enough to support life. Without this atmospheric blanket, Earth's average temperature would be about 33 degrees Celsius colder, turning our world into a frozen wasteland as our energy navigates through layers of varying temperature, pressure, and composition. It encounters the dynamic weather systems that make our atmosphere come alive. Massive air currents carry our energy horizontally across continents and oceans. Rising thermal columns lift portions of our energy high into the atmosphere, while descending air masses bring other portions closer to Earth's surface. The atmosphere doesn't just passively allow our energy to pass through, it actively participates in distributing this solar wealth across the planet. Clouds present some of the most dramatic interactions our energy will experience. When our solar radiation encounters a cloud, several things can happen simultaneously. Some of the energy reflects off the cloud's upper surface like sunlight bouncing off fresh snow, sending it back toward space without ever reaching the ground. Other portions penetrate into the cloud, where water droplets and ice crystals scatter the light in all directions, creating the soft diffused illumination we experience on overcast days. But clouds also trap heat. The infrared radiation that Earth emits back towards space gets absorbed by cloud droplets and re-radiated in all directions, including back down toward the surface. This is why cloudy nights often stay warmer than clear nights. Our energy becomes part of this complex dance of absorption, reflection, and re-emission that helps regulate Earth's temperature. The atmosphere also contains tiny particles called aerosols, microscopic bits of dust, pollen, sea salt, and pollution that float suspended in the air. Each of these particles interacts with our energy in unique ways. Some absorb certain wavelengths while reflecting others. Some act as nuclei around which water droplets form, leading to cloud formation. Others create the hazy conditions that can dramatically alter how our energy reaches the surface. During volcanic eruptions, these aerosol interactions become particularly dramatic. Massive quantities of tiny particles get injected high into the stratosphere, where they can remain for years, scattering and absorbing incoming solar energy. This can actually cool the planet's surface temporarily, demonstrating the delicate balance between incoming solar energy and atmospheric conditions. As our energy finally approaches Earth's surface after its journey through the atmospheric layers, it has been filtered, scattered, absorbed, and re-emitted multiple times. What started as raw nuclear energy in the sun's core has been transformed into the gentler warmth and light that sustains all life on our planet. The atmosphere has acted as both protector and moderator, ensuring that the energy reaching the surface is suitable for the delicate processes of life. After its 8-minute voyage through space and its complex dance through the atmosphere, our energy finally approaches the most crucial moment of its journey, the meeting with Earth's surface. This encounter, which happens billions of times every second across our planet, represents the transformation of cosmic energy into the warmth that will eventually reach your skin. But the story of how this happens is far more intricate and beautiful than we might first imagine. The first thing to understand is that Earth's surface is not a simple, uniform recipient of solar energy. Instead, our planet presents an incredibly diverse collection of materials, each with its own unique personality when it comes to interacting with incoming solar radiation. Some surfaces welcome our energy with open arms, absorbing it readily and converting it to heat. Others act more aloof, reflecting much of the energy back towards space. This fundamental difference in how surfaces respond to solar energy plays a crucial role in determining how our energy continues its journey. When our energy encounters fresh snow, something quite remarkable happens. Snow crystals, with their intricate six-sided symmetries and pristine white surfaces, reflect up to 90% of the incoming solar radiation back towards space. It's as if the snow is saying, "Thank you, but I have no need for your warmth right now." This high reflectivity, which scientists call albedo, helps explain why snow-covered regions stay cold even under bright sunshine. Most of our solar energy bounces harmlessly off the snow's surface, never getting the chance to warm the ground beneath. The ocean tells a very different story. When our energy meets the dark surface of seawater, up to 95% of it gets absorbed rather than reflected. The water molecules embrace our solar energy, converting it directly into molecular motion, which we experience as heat. But the ocean's interaction with our energy doesn't stop there. Water has an extraordinary capacity to store heat without dramatically changing temperature, a property that makes the ocean act like Earth's great thermal storage system. The energy that our photons deliver to the ocean's surface will eventually travel through ocean currents, carrying tropical warmth toward polar regions and moderating temperatures across the globe. Forests create their own unique interaction with our incoming energy. The dark green canopy of a healthy forest absorbs most of the solar radiation that reaches it. But unlike the ocean, trees use much of this energy for photosynthesis, the miraculous process that converts our solar energy into chemical energy, stored in plant tissues. In a very real sense, every leaf in a forest is a tiny solar panel, capturing our energy and transforming it into the sugars and starches that form the foundation of nearly all life on Earth. But trees do something else remarkable with our energy. Through transpiration, they release water vapor into the atmosphere, using our solar energy to power what amounts to a massive natural air conditioning system. A single large tree can transpire hundreds of liters of water per day, creating cooling effects that can be felt for considerable distances. Our solar energy, which began as nuclear fusion in the sun's core, now participates in the delicate regulation of local climate and weather patterns. Desert sand and rock surfaces interact with our energy in yet another fascinating way. These light-colored, dry surfaces absorb less solar energy than forests or oceans, but what they do absorb gets converted very efficiently to heat. Without water to moderate temperature changes, desert surfaces can become scorchingly hot during the day and surprisingly cool at night. Our energy heats the surface rapidly, and that same energy radiates back to space just as quickly once the sun sets. Urban environments create their own complex interactions with our solar energy. Concrete and asphalt absorb significant amounts of solar radiation, converting it to heat that gets stored in the massive thermal mass of buildings and pavement. This creates urban heat islands, areas where cities become significantly warmer than surrounding rural areas. Our energy becomes trapped in a maze of buildings and streets, bouncing between surfaces and gradually warming the entire urban environment. Ice presents one of the most critical interactions with our solar energy. Like snow, ice has a high albedo and reflects much of the incoming radiation back to space. But as our climate warms and ice melts, it exposes darker surfaces underneath, whether that's dark ocean water or bare ground. These darker surfaces absorb more of our solar energy, causing additional warming that melts more ice, which exposes more dark surface, creating what scientists call a positive feedback loop. Our energy becomes part of a self-reinforcing cycle that can dramatically alter Earth's climate systems. Agricultural land tells its own story of interaction with our solar energy. Farmers have learned to work with these energy exchanges, planting crops that can efficiently capture and use solar radiation for growth while managing the heat effects on both plants and soil. Green-growing plants absorb our energy for photosynthesis, while bare soil might reflect or absorb it, depending on its color, moisture content, and composition. The angle at which our energy strikes Earth's surface makes an enormous difference in how that energy is absorbed and used. At the equator, where the sun sits high overhead, our energy arrives nearly perpendicular to the surface, delivering maximum intensity per unit area. Near the poles, where the sun hangs low on the horizon, the same amount of energy gets spread over a much larger area, reducing its intensity and heating effect. This fundamental geometric relationship drives the temperature differences between tropical and polar regions that power our planet's weather systems and ocean currents. Seasonal changes add another layer of complexity to how Earth's surface interacts with our solar energy. As Earth orbits the sun, different regions of our planet tilt toward or away from the incoming radiation. During summer in the northern hemisphere, that region receives more direct solar energy and experiences longer days, while the southern hemisphere tilts away and experiences winter. Our energy becomes part of the seasonal rhythm that governs everything from plant growth cycles to animal migration patterns. The time of day also dramatically affects how our energy interacts with Earth's surface. In the early morning and late evening, our energy must travel through more atmosphere to reach the surface, getting filtered and scattered along the way. The energy that does arrive comes at steep angles, spreading its intensity over larger areas. Midday brings the most direct and intense delivery of our solar energy, creating the peak heating that drives most of Earth's weather patterns. But here's where our story takes a crucial turn. Not all of the solar energy that reaches Earth's surface stays there. Much of it gets re-radiated back toward space, but in a different form than it arrived. The visible light and shortwave infrared energy from the sun gets absorbed by Earth's surface and then re-emitted as longer wavelength infrared radiation, heat radiation that we can't see but can definitely feel. This re-emitted energy carries within it the story of its transformation. What began as high-energy photons from nuclear fusion has become gentler, longer wavelength radiation that rises from Earth's warming surface. Some of this heat radiation escapes directly to space, but much of it gets absorbed by greenhouse gases in the atmosphere, water vapor, carbon dioxide, methane, and others, which then re-radiate some of that energy back down toward the surface. This creates the greenhouse effect that keeps our planet warm enough to support life. Without this natural process, the average temperature on Earth would be far too cold for liquid water to exist at the surface. Our solar energy becomes part of a complex system of energy absorption, transformation, and re-radiation that maintains the delicate thermal balance necessary for life to flourish. The surface interactions we've described set the stage for the final portion of our energy's journey, its movement through the various materials and systems on Earth, until it finally reaches your skin as gentle warmth. But already we can see how our simple packet of nuclear energy has become part of Earth's most fundamental processes: weather and climate, the water cycle, photosynthesis, and the seasonal rhythms that govern life on our planet. Now comes the moment our radiant travelers have been journeying toward for 8 minutes and 20 seconds. After crossing the vast emptiness of space and dancing through the layers of our atmosphere, the heat energy finally reaches its destination, the surface of our beautiful blue planet. It's like watching the end of an epic voyage, where weary travelers finally glimpse the shores of their promised land. But Earth doesn't simply receive this gift of heat, energy passively. Oh no, our planet is far more sophisticated than that. Picture Earth as a master conductor, orchestrating one of the most complex symphonies in the universe. Every surface, every material, every texture responds to the sun's warmth in its own unique way, creating a magnificent choreography of energy. Transformation that has been playing out for billions of years. When those first rays of sunlight kiss the morning dew on a blade of grass, something magical happens. The grass blade, with its emerald green surface, absorbs some of the heat energy while reflecting others. It's like a selective doorman at an exclusive club, choosing which wavelengths get to enter and which must find another place to go. The darker the surface, the more heat it welcomes in. The lighter the surface, the more it politely sends back into the sky. Imagine walking barefoot on a summer day. You step from the cool, pale concrete of your driveway onto the dark asphalt of the street, and suddenly your feet tell a story of heat's incredible journey. That asphalt has been receiving and storing the sun's energy all day long, like a patient collector gathering treasures. The dark surface acts like a heat sponge, soaking up those precious photons and transforming them into the thermal energy that now warms the soles of your feet. But this is just the beginning of heat's earthly adventure. Once that solar energy makes contact with any surface on our planet, it begins a new chapter of its journey. It's no longer the same radiant energy that left the sun's surface. Now it has transformed, like a butterfly emerging from its chrysalis, into something entirely new, thermal energy. The kind of heat that can warm your hands over a campfire or make sand too hot to walk on at the beach. Consider for a moment. Incredible diversity of surfaces that welcome our sun's energy each day. There's the deep blue ocean, stretching endlessly toward the horizon, absorbing heat with the patience of eternity itself. The ocean doesn't just receive this energy and keep it. It cradles it, mixes it, and slowly releases it back into the atmosphere in an eternal dance of give and take. The water molecules begin to move more vigorously as they absorb the heat, like dancers responding to an increasingly energetic rhythm. Then there are the forests, those vast cathedrals of green that cover so much of our planet's surface. Each leaf is like a tiny solar panel, not just absorbing heat but using some of that energy to perform the miracle of photosynthesis. The trees take the sun's warmth and combine it with carbon dioxide and water to create the very oxygen we breathe. It's as if the forest is saying, "Thank you for this gift of heat, dear sun. In return, let me give life to all the creatures who call this planet home." The Rocky Mountains and stone cliffs tell their own story of heat reception. These ancient giants have been absorbing and releasing the sun's warmth for millions of years. During the day, the rocks slowly soak up the heat like massive stone batteries, storing it deep within their crystalline structures. Then, as the sun sets and the air grows cool, these stones become gentle heaters, slowly releasing their accumulated warmth back into the night air. It's why desert evenings can feel so comfortable even after blazingly hot days. The rocks are sharing their stored sunshine with the cooling world. Snow-covered peaks present us with one of nature's most beautiful examples of heat's interaction with Earth's surface. The brilliant white snow acts like a mirror, reflecting most of the sun's energy back towards space. It's nature's way of saying, "Thank you, but we're quite cool enough up here." This reflection, called albedo, is one of the ways our planet maintains its delicate temperature balance. The snow and ice fields serve as Earth's natural air conditioning system, helping to keep our planet from becoming too warm. But even in this reflection, there's poetry. Some of the sun's energy does penetrate the snow, causing those magical moments when sunlight seems to make fresh snow sparkle like millions of tiny diamonds. Each snow crystal acts like a miniature prism, breaking apart the sun's light and heat into component parts, creating those breathtaking winter scenes that make our hearts skip a beat. As heat energy settles into its new life on Earth's surface, it encounters an incredible library of materials, each speaking its own unique language of thermal behavior. It's like being introduced to a vast family where every member has their own personality, their own way of welcoming guests, and their own special talents for handling the precious gift of warmth. Let's begin with metals, those remarkable materials that seem to have a special relationship with heat. When you touch a piece of metal that's been sitting in the sun, you immediately understand something profound about heat's journey. The metal feels hot, sometimes almost burning hot, even though it might have been in the sun for just a short time. This isn't magic. It's the beautiful science of thermal conductivity. Metals are like the social butterflies of the material world when it comes to heat. Their atomic structure creates highways for thermal energy to travel along. Picture the metal as a bustling city where the atoms are connected by an intricate network of roads, and heat energy can zip from one atom to another with incredible speed. When heat touches one part of a metal object, it doesn't stay put like a shy wallflower. Instead, it races throughout the entire piece, sharing its warmth with every single atom it encounters. Iron, copper, aluminum. Each of these metals has its own speed limit for conducting heat. Copper is like the race car of the heat conduction world, moving thermal energy so quickly that it's used in cooking pots to ensure even heating. When you see a beautiful copper-bottom pan gleaming in the kitchen, you're looking at one of heat's favorite dance partners, a material that knows exactly how to take the sun's energy and distribute it evenly and efficiently. But contrast this with wood, and you discover an entirely different personality in the material world. Wood is the gentle, contemplative philosopher among materials. When heat energy arrives at a piece of wood, it's greeted with a completely different reception. The wooden surface warms slowly, almost thoughtfully, as if considering each molecule of heat energy before deciding where it should go next. This is because wood's structure is like a cozy cottage rather than a busy highway. The cellulose fibers create pockets and spaces that trap air, and air, as we've learned, is not eager to share heat quickly. So when you touch a wooden deck chair that's been sitting in the sun all day, it feels warm, but not burning hot like metal would. The wood has been patient with the heat, accepting it gradually and holding onto it gently. Stone and concrete tell yet another story in heat's earthly chapter. These materials are like the wise elders of the thermal world. They take their time with everything. When the morning sun first touches a concrete sidewalk, the surface begins a slow, steady process of heat absorption that will continue throughout the day. The thermal mass of these materials means they can store enormous amounts of heat energy, like massive libraries storing knowledge for future use. By midday, that concrete has become a significant heat reservoir. It's not just warm on the surface. The heat has slowly penetrated deep into the material, creating layers of stored thermal energy. This is why cities often stay warm well into the evening hours. All that concrete, asphalt, and stone has spent the day collecting the sun's gifts. And as night falls, these urban materials become gentle giants, slowly releasing their accumulated warmth back into the air. Glass presents us with one of the most interesting characters in heat's material adventures. Glass is like a selective translator, allowing some forms of energy to pass through while transforming others. When sunlight hits a window, most of the visible light passes through as if the glass weren't even there. But the heat? That's a different story entirely. Some of the heat energy passes through the glass, warming whatever lies beyond, which is why sitting by a sunny window can feel so wonderfully warm even on a cold day. But some of the heat is absorbed by the glass itself, causing the window to warm up. Touch a window that's been in direct sunlight, and you'll feel this absorbed heat energy. The glass has taken some of the sun's thermal gift and made it its own. This selective behavior of glass is what makes greenhouses possible. The glass allows the sun's energy to enter and warm the plants inside, but it also traps some of that heat, creating a warm environment even when the outside air is cool. It's like glass is saying to the heat energy, "Welcome, come on in, but you might want to stay a while and enjoy the warmth." Fabric and textiles add another delightful chapter to the story of heat and materials. When you hang a dark towel outside on a sunny day, you're witnessing heat's interaction with woven fibers. The cotton or linen fibers absorb the sun's energy, but they also trap air within their weave. This combination creates pockets of warm air that can make the towel feel toasty to the touch hours after you bring it inside. Different colors of fabric tell their own thermal stories. That black t-shirt hanging on the clothesline becomes significantly warmer than the white one hanging beside it. The dark fabric absorbs more of the sun's energy, welcoming heat like an old friend. The white fabric, meanwhile, reflects much of that energy back toward the sky, staying cooler in the process. It's the same principle that makes white cars cooler to touch than black cars on a sunny day. Water, that essential substance that covers most of our planet, has perhaps the most complex relationship with heat of any material we encounter. Water is like the diplomat of the thermal world. It accepts heat graciously, but it also demands a lot of energy to change its temperature. This property, called specific heat capacity, means that water can absorb large amounts of heat energy while warming up relatively slowly. When sunlight strikes the surface of a lake or ocean, the water begins a complex dance with heat energy. The surface water warms first, but water has another trick up its sleeve: convection. As the surface water warms, it becomes slightly less dense and wants to rise, while cooler water from below moves up to take its place. This creates gentle currents and circulation patterns that distribute the heat throughout the water body. As heat energy settles into the various materials of Earth's surface, it begins one of the most intimate and personal parts of its journey: conduction. This is where heat energy transforms from being simply absorbed to becoming truly mobile, traveling from atom to atom, molecule to molecule, in what might be described as the universe's most elegant relay race. Imagine heat conduction as a whispered message being passed from person to person in a long line. The message doesn't jump across empty spaces. It travels directly from one individual to the next, each person receiving the message, briefly holding it, and then passing it along to their neighbor. This is exactly how heat moves through solid materials, creating an unbroken chain of thermal communication that can carry warmth across great distances When you place your hand on a sun-warmed rock, you're experiencing the final moment of a journey that began deep within the rock structure. The surface atoms, energized by the sun's heat, began vibrating more vigorously hours ago. These excited atoms then bumped into their neighbors, sharing their energy and causing them to vibrate faster as well. This neighbor-to-neighbor energy transfer continued deeper and deeper into the rock until finally, the atoms touching your skin received the message and began their own energetic dance. But the speed of this atomic relay race varies dramatically depending on the material. In metals, the message travels at incredible speed because of those free electrons we mentioned earlier. These electrons act like express messengers, racing through the metal structure and carrying heat energy much faster than the atoms themselves could manage through simple vibration. This is why a metal spoon left in a hot cup of coffee becomes too hot to touch within seconds. The heat has raced up the handle faster than you can react. Picture a copper wire lying in the sun. As the sunlight warms one end of the wire, copper atoms there begin their thermal dance, vibrating with increased energy. But copper's electrons don't just sit still and watch this atomic celebration. They join the party with enthusiasm, absorbing some of this vibrational energy and carrying it along the wire like runners in a relay race. Within moments, the entire length of copper wire has become warm, even the parts that were shaded from. Direct sunlight. Wood tells a completely different story of heat conduction. When heat energy begins its journey through a piece of wood, it encounters a much more leisurely pace. The wooden structure is like a winding country road compared to metal's superhighway. The heat energy must travel from cellulose fiber to cellulose fiber, often having to navigate around air pockets and gaps in the wood structure. This slower pace isn't a disadvantage. It's one of wood's most valuable characteristics. When you hold a wooden spoon while stirring hot soup, the heat from the bowl doesn't race up to your hand because the wood is taking its time with the thermal energy transfer. The wooden spoon is protecting your hand by slowing down heat's journey, giving you time to cook without burning your fingers. Glass presents yet another fascinating example of heat conduction in action. When sunshine warms a window pane, the heat begins its journey from the outside surface toward the inside. But glass conducts heat relatively slowly, which is why you can touch the inside surface of a window and feel only gentle warmth, even when the outside surface is quite hot from direct sunlight. However, glass has an interesting characteristic. It's not uniform in its heat conduction. If there are imperfections, bubbles, or variations in thickness, heat will find the easiest paths to travel. This can create thermal stress, some parts of the glass expanding faster than others, which is why extremely hot glass sometimes cracks. The glass is essentially experiencing different rates of heat conduction in different areas, creating internal tension. Stone and concrete offer us a window into heat conduction over longer time scales. When the morning sun begins warming a concrete sidewalk, the heat energy starts its slow, steady journey into the material. Concrete is like a patient librarian, carefully cataloging and storing each bit of thermal energy it receives. The heat moves slowly but steadily, penetrating deeper and deeper into the concrete throughout the day. By afternoon, you can feel the results of this slow heat conduction. The surface is warm from the morning's heating, but there's also heat radiating from deeper within the concrete as the thermal energy continues its inward journey. This stored heat will continue conducting through the material well into the evening, which is why concrete and stone surfaces can still feel warm hours after the sun has set. The air itself presents an interesting case study in heat conduction. Air is what scientists call a poor conductor of heat, which means thermal energy moves through it very slowly through direct conduction. The air molecules are spread too far apart for efficient heat transfer through direct contact. When heat tries to travel through still air, it's like trying to pass a message through a crowd where everyone is standing too far apart to whisper to their neighbors. But this poor conductivity of air is actually one of the reasons we stay comfortable. The air trapped in our clothing acts as insulation, slowing down heat transfer and helping us maintain our body temperature. When you put on a thick winter coat, you're essentially surrounding yourself with trapped air that resists conducting heat away from your body. Soil tells its own unique story of heat conduction. The earth beneath our feet is composed of countless tiny particles, sand grains, clay pieces, organic matter, all mixed together with air and water. When sunlight warms the soil surface, heat begins conducting downward through this complex mixture. But the journey is slow and uneven because the heat must navigate around air pockets, through water droplets, and across the surfaces of mineral particles. Dry soil conducts heat differently than moist soil. Water, being a better conductor than air, creates pathways for heat energy to travel more efficiently. This is why garden soil that's been watered can feel warmer deeper down than dry soil. The water is helping to conduct the sun's heat further into the earth. The seasonal changes in our environment show us heat conduction on a grand scale. In winter, when snow covers the ground, we're witnessing heat conduction's protective power. The snow, filled with trapped air, acts as a blanket over the soil, slowing down the conduction of heat from the earth to the cold air above. Under this snowy insulation, the soil temperature remains relatively stable, protecting plant roots and soil organisms from the harsh cold of winter. As heat energy continues its earthbound journey, it discovers that conduction, while elegant, is not the only path available for travel. In fluids, liquids, and gases, heat energy finds a completely different mode of transportation: convection. If conduction is like passing a whispered message from person to person, then convection is like organizing a group dance where entire sections of dancers move together, carrying their energy and warmth with them as they flow. Picture a pot of water sitting over a campfire, receiving heat from the flames below. As the bottom layer of water warms up, something beautiful happens. The heated water becomes slightly less dense than the cooler water above it, and like a balloon filled with warm air, it wants to rise. This warmed water doesn't just sit there, getting hotter and hotter. It begins to move upward, creating gentle currents that carry heat energy throughout the entire pot. This is convection in its most visible form, the actual movement of heated material carrying thermal energy along with it. As the warm water rises, cooler water from higher up moves down to take its place near the heat source. Soon, you have established circulation patterns, rivers of warm water, flowing upward while streams of cooler water flow downward. The entire pot becomes a dynamic system of moving heat energy. The same principle works in air, though it's usually invisible to our eyes. On a sunny day, when the Earth's surface becomes warm from absorbing sunlight, the air directly above that surface begins to heat up. This warmed air, now less dense than the cooler air above it, starts to rise like invisible hot air balloons, launching into the sky. If you've ever watched birds soaring effortlessly in circles without flapping their wings, you've witnessed these thermal columns in action. The birds have found columns of rising warm air, thermals created by convection, and they ride these invisible elevators high into the sky. These graceful creatures are literally surfing on rivers of heat energy that began their journey as sunlight touching the Earth's surface. Ocean currents tell the grandest story of convection on our planet. The sun heats different parts of the ocean to different temperatures, and this uneven heating creates massive convection patterns that move warm water around the globe. The warm waters of the tropics, heated intensely by direct sunlight, begin moving toward the cooler polar regions, while the cooler waters from the poles flow toward the equator to replace them. These oceanic rivers of heat energy help distribute the sun's warmth around our entire planet. Without these convection currents, the tropics would be unbearably hot while the polar regions would be even colder than they already are. The ocean acts like a massive heat distribution system, using convection to share the sun's energy more evenly across Earth's surface. Even in the air above our heads, convection is constantly at work creating the weather patterns we experience every day. When the sun heats different parts of the land and ocean unevenly, it creates pressure differences that drive wind patterns. These winds are essentially convection currents on a massive scale, moving warm air from heated regions toward cooler areas. Consider what happens on a typical summer afternoon. The sun has been heating the dark asphalt of a parking lot all day, and by afternoon, that asphalt is quite hot. The air just above the asphalt becomes heated and begins to rise. As this warm air rises, it creates a slight vacuum that draws in cooler air from nearby areas. If you stand near the edge of a large parking lot on a hot day, you might feel these gentle breezes created by convection as cooler air flows in to replace the rising heated air. Inside buildings, convection plays a crucial role in how heat moves around rooms. When a heater warms the air near it, that air becomes less dense and rises toward the ceiling. This creates a circulation pattern where warm air rises along one side of the room while cooler air descends along the opposite side. Understanding these convection patterns is essential for efficient heating. It's why heaters are often placed near the floor and air conditioning vents near the ceiling. The human body uses convection in fascinating ways to regulate temperature. When we become warm, our blood vessels near the skin surface dilate, allowing more warm blood to flow close to the skin. This brings heat from deep within our bodies to the surface, where it can be released into the surrounding air. Our circulatory system acts like a personal convection system, moving heat from our core to our skin where it can escape. Cooking provides us with beautiful everyday examples of convection at work. When you bake bread in an oven, convection currents carry hot air around the loaf, ensuring even heating from all sides. Many modern ovens even have fans to enhance these natural convection currents, creating forced convection that cooks food more evenly and efficiently. The moving hot air transfers heat to the food much more effectively than still air would. Even the formation of clouds demonstrates convection on a grand scale. When the sun heats bodies of water, some of that water evaporates and rises into the atmosphere as invisible water vapor. As this warm, moist air rises higher and higher, it eventually reaches altitudes where the temperature is cool enough for the water vapor to condense back into tiny droplets. These droplets form the clouds we see, which are essentially visible markers of convection currents carrying heat and moisture high into the atmosphere. Fire itself creates dramatic convection currents. The intense heat from flames causes air to rise rapidly, creating the characteristic flickering and dancing motion we associate with fire. These convection currents not only carry heat upward, but also draw in fresh oxygen from below to feed the flames. A campfire is essentially a natural convection engine, using the movement of heated air to sustain itself while spreading warmth to everyone gathered around it. As our story of heat's journey continues, we encounter the third and perhaps most mysterious method of heat transfer: radiation. Unlike conduction, which requires direct contact, or convection, which needs a fluid medium to carry the heat, radiation travels through the complete emptiness of space, like a ghost carrying energy across impossible distances. This is the same method by which the sun's heat reached Earth in the first place, but now we see it happening on a much smaller, more intimate scale all around us. Every warm object in the universe is constantly broadcasting its thermal energy into space through electromagnetic radiation. It's as if every heated surface is a radio station, continuously transmitting its warmth to anyone willing to tune in and receive the signal. When you hold your hands near a campfire without touching the flames or even the hot air rising from them, you're experiencing radiant heat transfer. The glowing coals and dancing flames are emitting infrared radiation, invisible light waves that carry thermal energy directly to your skin. These waves don't need air to travel through. They speed across the space between the fire and your hands at the speed of light, delivering warmth instantly. This radiant energy is remarkably selective about what it heats. If you place a sheet of glass between yourself and the fire, you'll notice that the radiant heat is partially blocked, while the light from the flames passes through clearly. This happens because glass is transparent to visible light, but absorbs much of the infrared radiation that carries heat. The glass itself then warms up and begins radiating heat in all directions, including toward you. Every surface warmed by the sun becomes its own miniature heat broadcaster. That sun-warmed rock in your garden isn't just conducting heat to objects that touch it. It's also radiating thermal energy in all directions. If you sit near the rock as evening approaches, you can feel this radiant warmth on your face and hands. Even though you're not touching the stone directly, the color and texture of surfaces dramatically affect how much heat they radiate. Dark, rough surfaces are excellent radiators, efficiently broadcasting their thermal energy into the surrounding space. This is why a black asphalt road not only absorbs heat well during the day, but also radiates it effectively at night, creating those shimmering heat waves you sometimes see rising from hot pavement. Smooth, shiny surfaces tell a different story. A polished metal surface that has been warmed by the sun is actually quite poor at radiating that heat away. The same reflective properties that might make the surface appear cool to the eye also prevent it from efficiently broadcasting its thermal energy through radiation. This is why metals often feel hotter to the touch than you might expect. They're holding onto their heat rather than radiating it away. The human body is constantly involved in radiant heat transfer, though we're usually unaware of it. On a cool evening, your body is radiating heat into the surrounding air and surfaces. When you stand near a warm wall that has been heated by the sun all day, you receive radiant heat from the wall while simultaneously radiating your own body. Heat toward cooler surfaces. It's like being part of an invisible conversation where thermal energy is constantly being exchanged through electromagnetic radiation. This radiant heat exchange explains why identical air temperatures can feel dramatically different in different environments. Standing outside on a clear, cold night with a temperature of 40 degrees Fahrenheit feels much colder than standing in a room with the same air temperature. Outside, your body is radiating heat toward the vast cold sky with nothing radiating back toward you. Inside, the walls, ceiling, and floor are all close to room temperature and radiating warmth back in your direction. Snow-covered landscapes create fascinating examples of radiant heat dynamics. During the day, the brilliant white snow reflects most of the sun's radiant energy back towards space rather than absorbing it. But at night, that same snow becomes an efficient radiator, broadcasting any heat it has accumulated during the day back toward the cold, clear sky. This is why snow-covered nights can become extremely cold. The snow is actively radiating heat away from the Earth's surface. Greenhouses demonstrate radiant heat transfer in a particularly elegant way. The glass or plastic walls allow the sun's radiant energy to enter freely, where it's absorbed by the plants, soil, and structures inside. These heated surfaces then begin radiating heat, but much of this re-radiated energy is at wavelengths that the greenhouse materials don't transmit as easily. The result is that heat enters the greenhouse more easily than it can leave, creating the warm environment that plants love. Even clothing affects radiant heat transfer. Light-colored, loose-fitting clothes reflect radiant heat away from your body and allow heat to escape through radiation. Dark, tight-fitting clothes absorb more radiant heat and prevent your body from efficiently radiating its own heat away. This is why traditional desert clothing is often light-colored and flowing. It's designed to work with radiant heat transfer rather than against it. The evening hours provide some of the most beautiful demonstrations of radiant heat transfer. As the sun sets and direct solar heating ends, all the surfaces that absorbed heat during the day begin their own radiant performance. Rocks, pavement, buildings, and even the Earth itself start broadcasting their accumulated thermal energy back toward the cooling sky. This radiant cooling is why temperatures often drop most rapidly in the first few hours after sunset. Understanding radiant heat transfer helps explain why clear nights are often colder than cloudy ones. On a clear night, heated surfaces can radiate their energy directly towards space with nothing to stop them. But on a cloudy night, the water droplets in the clouds absorb some of this radiated heat and re-radiate it back toward Earth, acting like a thermal blanket that helps keep surface temperatures from dropping as quickly as our gentle heat continues its magnificent journey from the sun's heart to your skin. It must now learn to speak in three sacred languages, the ancient tongues of conduction, convection, and radiation. These are the messengers that carry thermal energy through every corner of our world, each with its own beautiful way of dancing through matter and space. Imagine, if you will, a whispered secret being passed from friend to friend in a long chain of trusted companions. This is conduction, the intimate, personal way that heat travels through solid materials. When the sun's warmth touches a rock, something magical happens. The molecules in that rock begin to vibrate with new energy, like children who've just heard exciting news. These vibrating molecules bump into their neighbors, sharing their excitement, and those neighbors bump into their neighbors. And so the message of heat spreads through the solid material, like ripples in a pond dotting metals. This process becomes even more enchanting. Metals have what we might call thermal ambassadors, free electrons that can dance freely through the metallic structure. These electrons are like swift messengers in a vast kingdom, carrying the news of heat from one end of the metal to the other with remarkable speed. This is why a metal spoon becomes warm so quickly when placed in hot soup, and why copper pots are treasured by cooks around the world. But heat is not content to travel only through solids in this intimate, molecule-to-molecule way. It has another, more flowing method of travel, convection. Picture a pot of water on a stove, and you'll witness one of nature's most beautiful dances. As the water at the bottom heats up, it becomes lighter, more buoyant, and begins to rise, like a thermal balloon. Meanwhile, the cooler water at the top, being denser, sinks down to take its place. This creates a circular current, a thermal carousel that carries heat throughout the liquid in graceful flowing patterns. The same principle works in the air around us. When the sun heats the ground, the air above it warms and rises, creating thermal currents that birds have learned to ride effortlessly. These convection currents are the reason why hot air balloons can soar through the sky, and why the air in your room naturally circulates, creating gentle drafts that help distribute warmth throughout your living space. But perhaps the most mysterious and wonderful of heat's languages is radiation, the same method by which the sun's energy first reached our planet. Unlike conduction and convection, radiation doesn't need any material medium to travel through. It's pure energy in motion, traveling at the speed of light through the vacuum of space. Every warm object in the universe, including your own body, constantly radiates infrared energy outward, like a lighthouse beaming its signal into the darkness. This radiation is why you can feel the warmth of a fire even when you're not touching it, and why your skin warms when you step into a sunny spot. The heat is literally traveling through the air as electromagnetic waves, requiring no air molecules to carry it. It's the universe's way of ensuring that thermal energy can reach everywhere, even across the vast emptiness of space. Now our story takes an extraordinary turn, for we must explore how heat behaves within the remarkable world of living systems. Every living creature on Earth is essentially a sophisticated thermal engine, constantly managing the flow of heat to maintain the delicate balance necessary for life. This is perhaps the most intricate and beautiful chapter in our heat's journey, as it transforms from a simple physical phenomenon into something that sustains the very essence of life itself. Consider the human body, a magnificent thermal symphony playing every moment of your life. Your body maintains a core temperature of approximately 98.6 degrees Fahrenheit, or 37 degrees Celsius, through an intricate system of thermal regulation that would make the most advanced engineering marvel seem simple in comparison. This temperature is not arbitrary. It represents the perfect balance point where the countless chemical reactions that sustain life can proceed at their optimal pace. Within each of your cells, tiny cellular furnaces called mitochondria are working tirelessly to convert the food you eat into usable energy. These microscopic powerhouses perform a process called cellular respiration, burning glucose and other nutrients with oxygen to produce ATP, the universal energy currency of life. But this process, like any combustion, produces heat as a byproduct. Far from being waste, this heat is essential to maintaining your body's temperature and enabling all of life's processes to function smoothly. Your circulatory system serves as the most elegant heat distribution network imaginable. Your heart pumps warm blood through an intricate network of vessels, carrying heat from your body's core to every extremity. As blood flows through your capillaries, it releases heat to the surrounding tissues, ensuring that even your fingertips and toes receive their share of life-sustaining warmth. This is why your pulse quickens when you're cold. Your body is working harder to circulate warming blood throughout your system. But your body is not just a passive recipient of heat. It's an active thermal manager. When you become too warm, your nervous system triggers several cooling mechanisms. Your blood vessels dilate, allowing more warm blood to flow near the surface of your skin, where heat can be lost to the environment. Your sweat glands activate, producing moisture that cools your skin through evaporation, the same process that cools a wet towel on a hot day. Even your breathing pattern changes, allowing you to lose heat through your lungs as you exhale warm, moist air. When you're cold, your body employs equally sophisticated warming strategies. Your blood vessels constrict, reducing heat loss through your skin. Your muscles may begin to shiver, rapid involuntary contractions that generate heat through movement. Your body may even activate brown fat tissue, a special type of fat that burns calories specifically to produce heat, much like a biological furnace. Plants, too, have their own fascinating relationships with heat. While they cannot regulate their temperature as actively as animals, they have evolved remarkable strategies to manage thermal energy. Some plants, like the Arctic willow, grow in low, cushion-like forms to conserve heat. Others, like the lotus flower, can actually generate their own heat through specialized metabolic processes, keeping their reproductive organs warm enough to attract pollinators even in cold weather. The thermal dynamics of living systems extend beyond individual organisms to entire ecosystems. Forests create their own microclimates, with the canopy providing shade that keeps the forest floor cool and moist. Hot springs support unique communities of thermophilic bacteria that thrive in temperatures that would be lethal to most life. Forms, even in the depths of the ocean where sunlight never penetrates. Hydrothermal vents create oases of warmth that support diverse communities of life. As our story draws closer to its ultimate destination, we must follow heat's final approach to the most sensitive and remarkable organ of your body, your skin. This is where the cosmic journey that began in the nuclear heart of the sun finally reaches its intimate conclusion, where energy that has traveled 93 million miles through space finally makes contact with the living boundary between your inner world and the vast universe beyond. Your skin is far more than a simple barrier. It's a sophisticated sensory organ that can detect and respond to thermal energy with extraordinary precision. Spread across your body's surface are millions of thermal receptors, tiny nerve endings that specialize in detecting temperature changes. These receptors are so sensitive that they can detect temperature differences as small as a fraction of a degree, allowing you to sense the gentle warmth of sunlight on your face or the cool touch of a breeze across your arms. There are two main types of thermal receptors in your skin: thermoreceptors that respond to warmth and those that respond to cold. The warm receptors, appropriately enough, are activated when your skin temperature rises above its normal range, while the cold receptors fire when temperature drops. But these receptors don't just detect absolute temperature. They're exquisitely sensitive to the rate of temperature change. This is why stepping from an air-conditioned room into summer heat feels so intense. Even though the temperature difference might be only a few degrees, the structure of your skin itself plays a crucial role in how heat reaches these receptors. Your skin consists of multiple layers, each with its own thermal properties. The outermost layer, the epidermis, is relatively thin, but acts as your first line of thermal defense. Beneath it lies the dermis, where most of your thermal receptors reside, embedded in a rich network of blood vessels that help regulate heat flow. The deepest layer, the hypodermis or subcutaneous tissue, contains fat cells that serve as thermal insulation, helping to maintain your body's core temperature. When heat from any source, whether it's the sun's radiation, warm air through convection, or a hot object through conduction, approaches your skin, it must first pass through the epidermis. This outer layer of skin cells acts like a thermal filter, moderating the rate at which heat can penetrate to the deeper layers where your thermal receptors wait. This protective mechanism prevents sudden temperature changes from overwhelming your sensory system and potentially causing damage. As heat penetrates deeper into your skin, it encounters the dense network of blood vessels in the dermis. These vessels can expand or contract in response to temperature, creating a dynamic thermal regulation system. When heat reaches your skin, these blood vessels dilate, allowing more blood to flow near the surface where heat can be dissipated to the environment. This is why your skin becomes flushed and warm when you exercise or spend time in the sun. The thermal receptors themselves are marvels of biological engineering. They are specialized nerve endings that can convert thermal energy into electrical signals that your brain can interpret. When heat activates these receptors, they generate electrical impulses that travel along nerve fibers to your spinal cord, and then to your brain. The frequency and intensity of these signals carry information about the temperature, duration, and location of the thermal stimulus. Your brain's interpretation of these thermal signals is incredibly sophisticated. It doesn't just register temperature. It integrates thermal information with other sensory data to create a complete picture of your environment. The warmth of sunlight on your skin becomes associated with visual brightness, the sounds of summer, and even emotional memories of pleasant times spent outdoors. This is why the feeling of warmth can be so deeply comforting and why thermal comfort is such an important component of overall well-being. The story of heat's journey would be incomplete without exploring how your brain transforms the simple physical phenomena of thermal energy into the rich, complex experience of thermal sensation. This transformation is where physics becomes psychology, where electromagnetic radiation becomes comfort, pleasure, or warning signals that guide your behavior and shape your daily experience. When thermal energy reaches your skin and activates your thermal receptors, it begins a cascade of neural processing that ultimately results in your conscious experience of warmth or coolness. But this process is far more complex and sophisticated than simply detecting temperature. Your brain must integrate thermal information from thousands of receptors across your entire body, weighing the signals from different regions and comparing them to your body's internal temperature set point. The sensation of warmth isn't just about absolute temperature. It's about the relationship between your body's internal state and the external thermal environment. This is why the same temperature might feel comfortable on one day and uncomfortably warm on another, depending on factors like humidity, air movement, your activity level, and even your emotional state. Your brain is constantly performing complex calculations to determine not just what temperature you're experiencing, but whether that temperature is appropriate for your current situation. Thermal comfort is a delicate balance influenced by 6 primary factors: air temperature, radiant temperature, humidity, air movement, clothing, and metabolic rate. Your brain unconsciously monitors all of these variables and adjusts your thermal perception accordingly. This is why you might feel comfortable in a cool room when you're wearing warm clothing, or why a gentle breeze can make a hot day feel pleasant. The psychological aspects of thermal sensation are equally fascinating. Your brain has developed strong associations between certain thermal experiences and emotional states. The warmth of a loved one's embrace, the comforting heat of a fireplace on a cold night, the refreshing coolness of a swimming pool on a hot day. These thermal experiences become deeply intertwined with memories, Emotions and feelings of safety and well-being. Research has shown that thermal comfort can influence your mood, productivity, and even your social behavior. When you're thermally comfortable, you're more likely to feel relaxed, focused, and positive. Conversely, thermal discomfort, whether from being too hot or too cold, can increase stress, reduce concentration, and even affect your immune system's ability to function effectively. Your body's thermal response system is also remarkably adaptive. Through a process called thermal acclimatization, your body can adjust its thermal sensitivity based on your regular thermal environment. People who live in hot climates develop increased tolerance for heat, while those in cold climates become more comfortable with lower temperatures. This adaptation occurs not just at the physiological level, but also at the perceptual level, as your brain recalibrates its thermal comfort zones based on your experiences. The cultural and social dimensions of thermal sensation add another layer of complexity to our story. Different cultures have developed varying relationships with heat and cold, influencing everything from architectural styles to clothing choices to social customs. The concept of thermal comfort itself varies across cultures, with some societies placing greater emphasis on individual thermal control while others prioritize collective thermal experiences. As we near the end of our journey, we must explore one of the most beautiful aspects of heat's relationship with human life: its power to heal and restore. Throughout human history, heat has been recognized not just as a source of comfort, but as a powerful therapeutic agent capable of promoting healing, reducing pain, and enhancing overall well-being. The therapeutic application of heat, known as thermotherapy, works through several mechanisms that demonstrate the profound connection between thermal energy and biological processes. When heat is applied to injured or painful areas of the body, it causes blood vessels to dilate, increasing blood flow to the affected region. This enhanced circulation brings oxygen and nutrients to damaged tissues, while helping to remove waste products and inflammatory compounds that contribute to pain and delayed healing. Heat therapy also has a direct effect on nerve transmission, following what's known as the gate control theory of pain. When heat stimulates the thermal receptors in your skin, it can actually block pain signals from reaching your brain. This is why a warm compress can provide immediate relief for muscle aches, and why heat therapy is often the first treatment recommended for various types of pain. The muscle relaxing effects of heat are particularly remarkable. When heat penetrates deep into muscle tissue, it increases the flexibility of collagen fibers, the protein structures that give muscles and connective tissues their strength and elasticity. This increased flexibility allows muscles to stretch more easily and reduces the tension that often contributes to pain and stiffness. The warmth also helps muscles release accumulated metabolic waste products, further contributing to pain relief and improved function. Different forms of heat therapy offer unique benefits. Dry heat, such as that provided by heating pads or infrared lamps, penetrates deeply into tissues and is particularly effective for muscle pain and stiffness. Moist heat, like that from warm baths or hot compresses, provides more superficial heating but can be more comfortable and is often preferred for treating skin conditions or surface injuries. The ancient practice of thermotherapy has found new expression in modern medical treatments. Diathermy uses high-frequency electromagnetic energy to generate heat deep within tissues, allowing for precise thermal treatment of specific areas. Ultrasound therapy converts sound waves into heat energy, providing targeted warming of deep tissues. These advanced techniques allow healthcare providers to deliver therapeutic heat with unprecedented precision and control. Sauna therapy represents one of the most comprehensive applications of therapeutic heat. Regular sauna use has been associated with numerous health benefits, including improved cardiovascular function, enhanced immune response, and reduced stress levels. The heat stress of a sauna triggers adaptive responses in your body that strengthen your cardiovascular system and improve your body's ability to cope with various forms of stress. The psychological benefits of heat therapy are equally important. The warmth of a therapeutic treatment can trigger the release of endorphins, your body's natural pain-relieving compounds. Heat therapy sessions often provide not just physical relief, but also emotional comfort, creating a sense of relaxation and well-being that supports the healing process. Hot water therapy, or balneotherapy, has been used for thousands of years across many cultures. Natural hot springs are rich in minerals that can be absorbed through the skin, providing additional therapeutic benefits beyond the effects of heat alone. The combination of warm water, mineral content, and the relaxing environment of a natural hot spring creates a powerful healing experience that addresses both physical and emotional needs. Even the simple act of taking a warm bath demonstrates the therapeutic power of heat. The warm water raises your body temperature slightly, triggering the release of heat shock proteins that help protect your cells from stress and damage. The buoyancy of the water reduces pressure on joints and muscles, while the heat helps relax tense muscles and calm the nervous system. Modern research continues to reveal new therapeutic applications for heat. Controlled hyperthermia is being investigated as a cancer treatment, using the cancer cell's sensitivity to heat to selectively destroy tumors while preserving healthy tissue. Heat therapy is also being explored as a treatment for depression, based on research showing that controlled elevation of body temperature can have antidepressant effects. The integration of heat therapy with other treatment modalities has created new possibilities for healing. Combining heat with massage therapy enhances the benefits of both treatments, as the warmth helps relax muscles and improve circulation, while the massage provides mechanical stimulation that further promotes healing. Similarly, heat therapy combined with exercise can improve flexibility and reduce the risk of injury while enhancing the benefits of physical activity. Perhaps most remarkably, heat therapy can be used not just to treat existing problems, but to prevent them. Regular exposure to mild heat stress, such as through sauna use or hot baths, can condition your body's heat response systems, improving your resilience to various forms of stress and potentially reducing your risk of cardiovascular disease, inflammatory conditions, and other health problems. The therapeutic applications of heat remind us that the journey of thermal energy from the sun to your skin is not just a physical process, but a fundamental aspect of health and healing. The same energy that powers our planet and sustains all life also has the power to restore and rejuvenate, to ease suffering and promote well-being. In this sense, every therapeutic application of heat is a continuation of the cosmic story that began billions of years ago in the heart of a star. As we contemplate these healing applications of heat, we begin to understand that the story of thermal energy is not just about physics and biology, but about the profound interconnectedness of all things. The energy that warmed the primordial earth and enabled life to emerge continues to sustain and heal us today, creating an unbroken chain of cosmic connection that links us to the very origins of the universe itself. This understanding transforms our experience of warmth from a simple physical sensation into something much more profound, a reminder of our place in the cosmic order, a connection to the fundamental forces that shape reality, and a tangible expression of the energy that flows through all things. When heat touches your skin, whether from the sun, a warm fire, or a therapeutic treatment, you are experiencing the culmination of a journey that began in the nuclear fires of stars and continues in the intricate dance of life itself. And so, our story of heat brings us to this moment, this gentle convergence where the cosmic energy that began its journey in the heart of our sun finally approaches its ultimate destination. After traveling across the vast emptiness of space, dancing through our atmosphere, warming our planet, and flowing through countless materials and living systems, heat energy now makes its final approach to something remarkably intimate: your skin. Picture yourself on a warm summer afternoon, perhaps sitting in a garden where the light filters through leaves and shifting patterns of brightness and shadow. The heat that touches your face in this moment carries with it the entire story we have been exploring together. Every photon that caresses your cheek began its existence deep within the sun's core, where temperatures soar beyond imagination and nuclear fusion creates the very energy that now dances across your skin with such gentle warmth that your skin, this remarkable boundary between your inner world and the vast universe beyond, stands ready to receive this cosmic gift. It is not merely a passive recipient, but an active participant in this ancient dance of energy transfer. The surface of your skin, with its intricate landscape of pores, fine hairs, and microscopic ridges, creates a complex interface where heat energy can arrive through multiple pathways simultaneously. Consider the direct radiation from the sun as it strikes your skin. These electromagnetic waves, traveling at the speed of light, carry their energy across the final millimeters of their journey through the thin layer of air that surrounds your body. The infrared radiation, invisible to your eyes but deeply felt by your skin, penetrates slightly into the outer layers of your epidermis, where it sets molecules vibrating with increased energy. This is the moment of direct energy transfer, where the motion of atoms that began in the sun's core finally communicates itself to the atoms that make up your very being. But this is only one part of the story. The warm air that surrounds your body carries its own thermal energy, energy that has been gathered from surfaces warmed by the sun throughout the day. As gentle breezes move across your skin, they bring with them heat that has been collected from sun-warmed stones, heated pavement, and the warm earth itself. This convective heat transfer adds another layer to the thermal symphony that plays across your skin's surface. Then there is the radiant heat from all the objects around you that have been warmed by the sun's energy throughout the day. The wooden bench you might be sitting on, the metal railing nearby, the leaves of the trees, even the ground beneath your feet. All of these surfaces have absorbed solar energy and are now gently radiating it back into the environment. Your skin receives this secondary radiation, this reflected and re-emitted thermal energy that represents the sun's gift being shared and reshared throughout the world around you. As these various forms of heat energy approach your skin, something beautiful begins to happen. Your body's most sophisticated sensory system starts to respond to this thermal information with a complexity that rivals the most advanced technologies humans have ever created. The story of heat becomes a story of sensation, of awareness, of the remarkable way your body interprets and responds to the thermal energy that surrounds it. Your skin is far more than a simple barrier between inside and outside. It is a vast sensory landscape, a living interface that contains millions of specialized receptors designed to detect and interpret thermal energy. Stretched across the approximately 2 square meters of an adult human body, your skin contains one of the most sophisticated thermal detection systems in the natural world. Within the deeper layers of your skin, nestled among the networks of blood vessels, nerve fibers, and connective tissues, lie the thermoreceptors, specialized nerve endings that exist for the sole purpose of detecting changes in temperature. These remarkable sensors come in different varieties, each tuned to respond to specific aspects of thermal energy. Some respond primarily to warming, others to cooling, and still others to rapid temperature changes that might signal danger or opportunity. When heat energy from our solar journey finally reaches these thermoreceptors, it triggers a cascade of responses that transform physical energy into electrical signals. The warming of your skin causes specific ion channels in these sensory neurons to open, allowing electrical current to flow along nerve pathways toward your brain. This is the moment when the story of heat becomes a story of perception, when physical energy transforms into conscious awareness. But the skin's response to heat is not uniform across its surface. Different areas of your body contain different densities of thermoreceptors, creating a varied landscape of thermal sensitivity. Your face, particularly around your lips and nose, contains some of the highest concentrations of temperature-sensitive nerve endings. This is why a gentle warm breeze feels so pleasant on your face, why the sun's warmth seems most noticeable when it touches your cheeks. Your fingertips, too, are exquisitely sensitive to temperature changes. When you reach out to touch a surface that has been warmed by the sun, your fingertips can detect temperature differences as small as a fraction of a degree. This sensitivity serves an important evolutionary purpose, helping you assess the safety and comfort of your environment through the simple act of touch. The palms of your hands and the soles of your feet contain their own unique thermal signatures. These areas, constantly in contact with the world around you, have evolved to provide detailed thermal information about the surfaces you touch and walk upon. When you walk barefoot on sun-warmed sand, the thermal energy transfers through the soles of your feet in patterns that your brain interprets not just as warmth, but as texture, safety, and comfort. Your scalp, often exposed to direct sunlight, contains specialized adaptations for dealing with thermal energy. The hair follicles and sebaceous glands in this area work together to manage temperature, while the blood vessels just beneath the surface can dilate or constrict to help regulate the amount of heat that reaches the deeper tissues of your head. Even your clothing plays a role in this thermal story. The fabric that covers your skin creates its own microenvironment, trapping air that has been warmed by your body heat while also filtering and modifying the thermal energy that reaches you from the outside world. The space between your clothing and your skin becomes a small climate system, where heat energy circulates and creates patterns of warmth and coolness that your skin detects and responds to. As heat energy settles into this complex landscape of your skin, it begins to influence not just your sensory experience, but your entire physiological state. The warming of your skin triggers responses throughout your body's systems, from your cardiovascular system to your nervous system, creating a whole body response to the thermal energy that originated so far away in the heart of our sun. When heat energy finally makes contact with your skin, it begins to speak in a language that your body has been learning to understand for millions of years of evolution. This is not the language of words or symbols, but the ancient language of thermal sensation. a communication system that operates below the level of conscious thought that profoundly influences your experience of comfort, safety, and well-being. The first words in this thermal language are spoken by the immediate receptors in your skin's outer layers. As heat energy begins to warm these tissues, specialized nerve endings called warm receptors start to increase their activity. These receptors don't simply detect the presence of heat. They detect the rate of temperature change, the intensity of the thermal energy, and even the pattern of warming across different areas of your skin. This thermal information travels along nerve pathways that have been refined over countless generations. The electrical signals generated by your thermoreceptors race along nerve fibers at speeds of up to 120 meters per second, carrying their thermal messages toward your spinal cord and brain. This is remarkable when you consider that the heat energy itself, which began its journey at the speed of light in the form of electromagnetic radiation, has now been transformed into electrical signals that travel through your nervous system at a much slower, but still impressive pace. As these thermal signals reach your spinal cord, they encounter the first processing centers in your nervous system. Here, the raw thermal information begins to be interpreted and integrated with other sensory data. Your spinal cord doesn't just passively relay this information. It actively processes it, filtering out background thermal noise and amplifying signals that might be important for your safety or comfort. The thermal signals that continue their journey toward your brain carry with them not just information about temperature, but a rich tapestry of data about your thermal environment. They indicate not only that warmth is present, but where it is located on your body, how intense it is, whether it is increasing or decreasing, and how it compares to the thermal baseline that your body maintains as its reference point. When these thermal messages finally reach your brain, they are received by multiple regions simultaneously. The somatosensory cortex, responsible for processing touch and temperature sensations, begins to create a thermal map of your body's surface. This map is constantly updated as new thermal information arrives, creating a dynamic, ever-changing picture of your body's thermal state. But the thermal information doesn't stop there. It also reaches the limbic system, the ancient part of your brain responsible for emotions and basic drives. Here, the warmth on your skin begins to influence how you feel, not just physically but emotionally. There is a reason why we associate warmth with comfort, safety, and well-being. The gentle heat that touches your skin can trigger the release of neurotransmitters that promote relaxation and contentment. Your hypothalamus, the master controller of your body's temperature regulation system, also receives this thermal information. This small but crucial region of your brain continuously monitors thermal input from all over your body, using this information to make decisions about how to maintain your optimal body temperature. When the warm sun touches your skin, your hypothalamus notes this external heat source and may adjust your body's internal heating and cooling mechanisms accordingly. The language of warmth also includes important messages about social and emotional connection. Throughout human evolution, shared warmth has been associated with safety, community, and care. The thermal sensors in your skin don't just detect physical temperature. They contribute to feelings of comfort and belonging that have deep evolutionary roots. When you feel the sun's warmth on your skin, part of your brain's response echoes the ancient comfort of sharing warmth with others, of being in a safe and nurturing environment. This thermal language even influences your perception of time and space. The gradual warming of your skin as you move from shade into sunlight, or the slow cooling as evening approaches, provides your brain with subtle cues about the passage of time and your movement through space. Your thermal sensors contribute to your spatial awareness, helping you understand your position relative to heat sources and thermal gradients in your environment. As the story of heat from our sun reaches this intimate moment of contact with your skin, your body responds with a symphony of physiological adjustments that demonstrate the remarkable integration between external thermal energy and internal biological processes. This response involves every major system in your body, from your cardiovascular system to your endocrine system, creating a whole body adaptation to the thermal gift that has traveled so far to reach you. The most immediate response occurs in the blood vessels just beneath your skin's surface. As heat energy warms your skin, these tiny vessels, called capillaries, begin to dilate in a process known as vasodilation. This response is automatic and precise, controlled by both local thermal sensors and signals from your brain's temperature regulation centers. As these blood vessels expand, more warm blood from your body's core flows closer to the surface, creating a beautiful biological heat exchange system. This vasodilation serves multiple purposes in your body's thermal story. First, it allows your body to release excess heat when external temperatures are high, helping to maintain your optimal internal temperature. But it also creates the lovely warm sensation you feel when heat energy reaches your skin. The increased blood flow brings with it not just thermal energy, but also nutrients and oxygen that nourish your skin cells, creating a sense of vitality and well-being. Your sweat glands, those remarkable microscopic structures distributed across your skin's surface, may also begin to respond to the thermal energy. Even before you become consciously aware of being warm, these glands start to produce tiny amounts of moisture. This isn't yet the obvious sweating that occurs during intense heat or exercise, but rather a subtle increase in skin moisture that helps optimize heat transfer and maintain your skin's healthy function. The hair follicles on your skin also participate in this thermal response. The tiny muscles attached to each hair follicle, called erector pili muscles, relax when your skin is warmed. This is the opposite of what happens when you're cold and get goosebumps. When these muscles relax in response to warmth, your hair lies flat against your skin, optimizing the surface area available for heat exchange and creating the smooth, relaxed feeling of warm skin. Your nervous system's response to thermal energy extends far beyond the initial detection and sensation. The warming of your skin triggers the release of various neurotransmitters and hormones that influence your mood, alertness, and overall sense of well-being. Serotonin, often called the happiness neurotransmitter, can be influenced by thermal sensation, which is part of why warm, sunny days often make people feel more positive and energetic. Your body's production of vitamin D also becomes part of this thermal story. While vitamin D synthesis is primarily triggered by ultraviolet radiation rather than heat, the two often arrive together in sunlight. As your skin warms in the sun, it may simultaneously be producing this crucial vitamin that supports bone health, immune function, and many other biological processes. The thermal sensation of warmth thus becomes associated with this important biological synthesis that your circadian rhythm system, controlled by light-sensitive cells in your eyes and influenced by thermal cues throughout your body, also responds to the thermal energy reaching your skin. The warming of your skin during daylight hours helps reinforce your body's natural daily cycle, supporting healthy sleep patterns and optimal hormone production. The thermal story of heat from the sun, thus, becomes intimately connected with your body's natural rhythms and cycles. Even your immune system participates in the response to thermal energy. Mild warming of the skin can stimulate the activity of certain immune cells, supporting your body's natural defense systems. This may be one reason why moderate exposure to warm sunlight is associated with various health benefits, from improved wound healing to enhanced resistance to certain infections. Your digestive system, too, may be influenced by the thermal energy reaching your skin. The complex network of nerves that connects your skin to your internal organs can carry thermal information that influences appetite, digestion, and metabolism. The warmth of the sun on your skin can contribute to the relaxed, comfortable state that optimizes digestive function and nutrient absorption. Your respiratory system also responds to thermal changes. As your skin warms, your breathing may naturally become slower and deeper, supporting the relaxed state that warmth promotes. The thermal receptors in your skin communicate with the brain centers that control breathing, creating a gentle unconscious adjustment that enhances the peaceful feeling of being warmed by the sun. There comes a moment in the story of heat from the sun to your skin when all the elements align in perfect harmony. This is the moment when the thermal energy that began its journey in the nuclear fires of our star reaches the ideal balance with your body's own thermal systems, creating that sensation we simply call comfortable warmth. It is a moment that represents the culmination of our entire thermal journey, a perfect convergence of cosmic energy and human biology. This moment might find you sitting quietly in a garden, where the afternoon sun filters through leaves in a gentle dance of light and shadow. The thermal energy reaching your skin in this moment is precisely calibrated by nature itself, not too intense to cause discomfort, not too weak to go unnoticed, but just right to create that sense of perfect thermal balance that makes you want to close your eyes and simply exist in the pure pleasure of the sensation. In this moment, your thermoreceptors are active but not overwhelmed. They are detecting the gentle warming of your skin and translating it into electrical signals that your brain interprets as pure comfort. There is no thermal stress, no need for your body to activate cooling mechanisms or warming responses. Instead, there is a perfect equilibrium between the heat energy arriving from outside and your body's internal thermal state. Your blood vessels have found their optimal dilation, allowing just the right amount of warm blood to flow near your skin's surface. This creates a gentle internal glow, a sense of vitality and well-being that comes from optimal circulation. Your skin feels alive and healthy, neither too warm nor too cool, but perfectly matched to the thermal environment around you. Your breathing, in this moment, naturally deepens and slows. The comfortable warmth signals to your nervous system that all is well, that you are in a safe and nurturing environment. Your heart rate may settle into a peaceful rhythm, your muscles may relax, and your mind may naturally become calmer and more focused. This is the gift of perfect thermal balance. It creates the conditions for both physical and mental well-being. The thermal energy touching your skin in this moment carries with it the entire story we have explored together. Every photon warming. Your face began its existence in nuclear fusion reactions that combined hydrogen into helium, releasing energy that would eventually travel across 93 million miles of space to reach this perfect moment of contact with your skin. The warmth you feel is literally the touch of stellar energy, a direct connection between your human experience and the cosmic processes that power our solar system. This thermal energy has survived the journey through the vacuum of space, where temperatures hover just above absolute zero. It has navigated the complex dance with our atmosphere, some of it absorbed and scattered, some of it transmitted through to reach the surface. It has interacted with the materials of our world, warming surfaces, heating air, and creating the complex thermal environment that surrounds you. And now, in this moment of perfect warmth, it completes its journey by becoming part of your sensory experience, part of your physical and emotional state, part of the complex biological processes that maintain your life and health. The energy that began in the heart of a star has become an integral part of your human experience. This moment also represents a connection to every other living thing that has ever basked in the warmth of our sun. The same thermal energy that warms your skin has warmed countless generations of humans before you. It has provided the energy that drives photosynthesis in plants, creating the oxygen you breathe and the food you eat. It has evaporated water to create the rain that fills our rivers and lakes. It has created the weather patterns that shape our planet's climate. In this moment of perfect warmth, you are participating in one of the most fundamental processes in our solar system, the transfer of energy from our star to the worlds that orbit it. You are part of a vast energy system that connects the sun to every corner of our planet, a system that has been operating for billions of years and will continue long after we are gone. The thermal sensation you experience in this moment is both intensely personal and universally shared. It is your individual nervous system responding to heat energy, creating a sensation that is uniquely yours. Yet it is also part of the common human experience of warmth, comfort, and connection to the natural world. Every person who has ever felt the pleasant warmth of the sun has shared in this same fundamental experience. As we near the end of our story of heat from the sun to your skin, it becomes clear that this is not really an ending at all, but rather a moment in an endless cycle that connects all life on Earth to the energy of our star. The thermal energy that has just finished its journey to your skin is already beginning new journeys, new transformations, new stories of energy and life. Some of the heat energy that reaches your skin will be absorbed by your body, where it will become part of the thermal energy that maintains your body temperature. This energy will support the biochemical processes that keep you alive, from the metabolism in your cells to the circulation of blood through your body. In this way, the energy from our sun becomes literally part of your life force, part of the energy that powers your thoughts, movements, and dreams. Other thermal energy will be reflected from your skin back into the environment, where it will continue its journey in new forms. This reflected energy may warm the air around you, contributing to the thermal currents that create gentle breezes. It may be absorbed by nearby plants, where it will support photosynthesis and the growth of new life. It may warm other surfaces, which will in turn radiate their own thermal energy, creating an endless web of energy transfer and transformation. The moisture that your skin releases in response to thermal energy will carry heat away from your body through evaporation, adding to the water vapor in the atmosphere. This water vapor will eventually condense into clouds, and the heat energy it carries will be released high in the atmosphere, contributing to weather patterns and the global circulation of air masses. The energy that touched your skin thus becomes part of the vast atmospheric engine that drives our planet's weather and climate. Your body's response to the thermal energy will also continue to unfold long after the initial moment of warming. The vitamin D that may have been synthesized in your skin during sun exposure will support your bone health and immune function for days or weeks to come. The relaxation response triggered by comfortable warmth may improve your sleep quality and support your mental well-being long after the thermal sensation has faded. The thermal energy that warms your skin also connects you to the broader cycles of our planet. As day turns to night, the surfaces around you that have been warmed by the sun will slowly release their stored thermal energy back into the cooling atmosphere. This daily cycle of heating and cooling drives many of the natural processes that shape our world, from the formation of morning dew to the evening breezes that cool our summers. On a longer timescale, the thermal energy from our sun drives the seasonal cycles that bring spring warmth, summer heat, autumn cooling, and winter cold. Your skin's experience of thermal energy is part of this grand seasonal dance, connecting your daily experience to the vast cycles of our planet's journey around the sun. The warmth you feel on a spring day carries with it the promise of summer's abundance, while the fading warmth of autumn speaks of winter's approach and the eternal cycle of renewal. Even the thermal energy that seems to be lost to space continues its journey. The infrared radiation that your skin emits as it cools will travel outward from Earth, carrying energy back toward the cosmos from which it came. Some of this energy will be absorbed by the atmosphere, contributing to the greenhouse effect that keeps our planet warm enough to support life. Some will escape to space, carrying the thermal signature of our living world to the cold depths of the universe. This endless cycle of thermal energy connects us not only to our sun, but to the entire universe. The heavy elements that make up your body were forged in the nuclear fires of ancient stars, stars that produced thermal energy much like our sun does today. The calcium in your bones, the iron in your blood, the carbon in your DNA, all of these elements were created in stellar furnaces and scattered through space when those ancient stars ended their lives in spectacular explosions. In this way, the story of heat from the sun to your skin is also the story of your connection to the cosmos itself. You are made of star stuff, warmed by starlight, participating in the endless dance of energy that connects all matter in the universe. The thermal sensation you experience when the sun warms your skin is a reminder of this cosmic connection, a gentle touch that links your individual experience to the vast processes that govern stars, planets, and the evolution of life itself. As our journey through the story of heat draws toward its gentle conclusion, we find ourselves contemplating not just the science of thermal energy, but the poetry inherent in this cosmic connection between star and skin. There is something profoundly beautiful about the fact that the energy warming your face on a pleasant afternoon began its existence in nuclear reactions that occur at temperatures beyond human comprehension, yet ends its journey as the gentlest caress of warmth against your cheek. This poetry lies in the transformation itself, the way pure energy can travel across the emptiness of space, dance through our atmosphere, warm our world, and ultimately become part of our sensory experience, our emotional state, our very sense of being alive and connected to the world around us. It is a poetry written in the language of physics, but felt in the realm of human experience and emotion. Consider the exquisite timing involved in this thermal story. The nuclear reactions that created the energy now warming your skin occurred in the sun's core over many thousands of years ago, as the energy slowly worked its way from the center of our star to its surface. The final 8-minute journey from the sun to Earth represents just the conclusion of a much longer story that began deep in stellar time, yet this ancient energy arrives at precisely the right moment to contribute to your experience of this day, this hour, this moment. The warmth that touches your skin right now carries with it the history of our solar system, the story of stellar evolution, and the complex dance of energy that makes life possible on our planet. In feeling this warmth, you are participating in a story that is billions of years old, yet eternally present. The poetry also lies in the perfect calibration of this thermal system. Our sun produces just the right amount of energy to warm our planet without overheating it. Our atmosphere provides just the right amount of filtering and moderation to make solar energy beneficial rather than harmful. Our bodies have evolved the perfect sensitivity to detect and respond to thermal energy in ways that support our health and well-being. This is not coincidence, but rather the result of billions of years of evolution and adaptation. Life on Earth has shaped itself around the thermal energy provided by our sun, and in doing so, has created the conditions for the exquisite sensitivity to warmth that allows you to experience comfort, pleasure, and connection through the simple sensation of thermal energy on your skin. The poetry extends to the way thermal energy connects us to each other and to all life on Earth. The same sun that warms your skin also warms every other living thing on our planet. The thermal energy you feel connects you to the plants that grow in solar-powered photosynthesis, to the animals that bask in the sun's warmth, to the microorganisms that depend on solar energy for their survival. When you feel the warmth of the sun on your skin, you are participating in the same fundamental process that has sustained life on Earth for billions of years. You are part of an unbroken chain of thermal connection that links you to every organism that has ever lived on our planet. From the earliest photosynthetic bacteria to the complex ecosystems of today, there is poetry, too, in the way thermal sensation connects us to our emotions and memories. The warmth of the sun can trigger memories of childhood summers, of peaceful moments in gardens, of times when we felt safe and cared for. The thermal energy that reaches your skin carries with it not just physical warmth, but the capacity to evoke feelings, memories, and states of mind that contribute to your overall sense of well-being and connection to life. This emotional dimension of thermal experience speaks to the deep integration between our physical and psychological selves. The energy that began in nuclear fusion reactions and traveled across space to reach your skin doesn't just warm your body, it can warm your heart, lift your spirits, and connect you to feelings of peace, contentment, and belonging. The poetry of heat also lies in its universality and its intimacy. Every human being has experienced the sensation of warmth on their skin. It is one of our most fundamental and shared sensory experiences. Yet each person's experience of thermal sensation is also unique, filtered through their individual nervous system, their personal history, their current emotional state, and their particular circumstances. In this way, the story of heat from the sun to your skin is both a cosmic story and a deeply personal one. It connects you to the vastness of space and time, to the fundamental processes that govern our universe, and to the long history of life on Earth. Yet it also speaks to your individual experience, your personal relationship with the natural world, and your own unique capacity for sensation, emotion, and awareness. In these final moments of our story, as we contemplate the complete journey of heat from the sun to your skin, we arrive at a profound realization. Every time you feel the warmth of sunlight on your body, you are literally being touched by a star. This is not metaphor or poetry, but scientific fact. The energy that creates the sensation of warmth on your skin originated in the nuclear furnace of our sun and has traveled across the vast emptiness of space to make physical contact with your body. This stellar touch is remarkably gentle considering its origins. The same nuclear processes that could vaporize any known material, that create temperatures hot enough to fuse atomic nuclei, that generate energies beyond human comprehension, ultimately manifest as the softest caress of warmth against your cheek. The sun's power, filtered through space and atmosphere, moderated by distance and time, arrives at your skin as a gift of comfortable warmth rather than destructive heat. When you close your eyes and turn your face toward the sun, feeling that familiar warmth spread across your skin, you are experiencing one of the most direct connections possible between human consciousness and the cosmic processes that power our universe. The photons striking your face have traveled from the heart of a star, carrying with them the signature of nuclear fusion, the fingerprint of stellar evolution, the essence of the cosmic dance that creates and sustains all the energy in our solar system. This stellar touch connects you not only to our sun, but to the broader community of stars that fills our galaxy and beyond. Every star in the night sky is engaged in the same fundamental process, converting matter into energy through nuclear fusion, radiating that energy into space, potentially warming worlds and touching lives in ways we can barely imagine. Our sun is just one of hundreds of billions of stars in our galaxy, each one a potential source of the same stellar touch you feel when sunlight warms your skin. The touch of our star also carries with it the story of stellar evolution, the remarkable process by which stars are born, live, and eventually die, creating and dispersing the elements that make up planets and life itself. The sun that touches your skin today is in the prime of its life, steadily converting hydrogen into helium and releasing the energy that makes life on Earth possible. But it is also a temporary visitor in the cosmic landscape, destined to evolve and change over billions of years. In about 5 billion years, our sun will begin to run out of hydrogen fuel in its core and will start to evolve into a red giant star. During this phase, it will expand to enormous size, eventually engulfing the inner planets of our solar system. The gentle stellar touch you feel today will become a blazing embrace that will transform our entire solar system. Yet even in this dramatic future, the same fundamental process will be at work. Nuclear energy created in the heart of a star, radiating outward to touch and transform the worlds around it. The stellar touch you experience also connects you to the past, to the earlier stages of our sun's life when it was younger and perhaps slightly different in its energy output. The warmth that has touched countless generations of life on Earth has always carried this same stellar signature. This same fundamental connection between nuclear fusion and the sensation of comfort and warmth on living skin. Every plant that has ever grown in sunlight, every animal that has ever basked in solar warmth, every human being who has ever felt the pleasure of the sun's rays, all have experienced this same stellar touch. You are part of an unbroken chain of life that has been warmed and sustained by stellar energy for billions of years, connected through the sensation of warmth to the deepest processes of cosmic evolution. The immediacy of this stellar touch is remarkable. When you feel the sun's warmth, you are experiencing something that left the sun's surface just 8 minutes ago. The energy touching your skin is younger than many of the thoughts you've had today, yet it originated in nuclear processes that represent the fundamental source of energy in our universe. You are experiencing, in real time, the arrival of stellar energy that has just completed its journey from star to skin. The stellar touch also carries with it the signature of the space it has traveled through. The energy warming your skin has crossed the vast emptiness between worlds, has passed through regions where temperatures approach absolute zero, where matter is incredibly sparse, where the silence is absolute. Yet it arrives at your skin carrying the warmth and energy of stellar fire, a testament to the fundamental nature of radiant energy and its ability to carry information and sensation across the cosmos. In feeling this stellar touch, you are participating in one of the most ancient and fundamental relationships in the universe, the relationship between stars and the worlds they illuminate. This relationship has shaped the evolution of our solar system, the development of our planet, the emergence of life, and the very conditions that allow you to exist and experience the warmth of starlight on your skin. The touch of stars is both a daily experience and a cosmic privilege. Every clear day offers you the opportunity to feel this stellar connection, to experience the gentle power of nuclear fusion transformed into the simple pleasure of warmth on your skin. Yet it is also a profound reminder of your place in the universe, your connection to the fundamental processes that govern stars and planets, and your participation in the ongoing story of cosmic evolution. As our story of heat from the sun too. Your skin draws to its close. We are left with this beautiful truth. You are touched by stars every day, warmed by nuclear fusion, caressed by energy that has traveled across space to reach you. In the gentle sensation of solar warmth on your skin, you experience one of the most direct and intimate connections possible between human consciousness and the cosmic processes that power our universe. You are, quite literally, being embraced by the universe itself. Thank you for staying with me through this peaceful journey into the story of heat. From the sun to your skin, I hope that the next time you feel the warmth of sunlight on your face, you'll remember this story we've shared together. You'll remember that the sensation you're feeling connects you to nuclear fusion in the heart of our star, to the vast journey of energy across space, to the complex dance of thermal energy through our atmosphere and across our planet, and finally, to the remarkable sensitivity of your own skin and nervous system. In that moment of warmth, you'll know that you're participating in one of the most fundamental and beautiful processes in our universe, the journey of stellar energy from the heart of a star to the consciousness of a living being. You'll know that you're being touched by the cosmos itself, warmed by processes that have been sustaining life on Earth for billions of years, connected through sensation to the deepest mysteries and most essential truths of our existence. Story of heat is ultimately the story of connection. Connection between star and planet, between energy and life, between the cosmic and the intimate, between the vast processes of the universe and the gentle sensation of warmth on your skin. It's a story that reminds us that we are not separate from the universe, but intimately connected to it, warmed by it, sustained by it, and forever part of its ongoing story of energy, transformation, and life. May you carry this story with you, and may it add a sense of wonder and connection to every moment when you feel the sun's gentle warmth on your skin. Until we meet again for another peaceful journey through the beautiful mysteries of our world, take care, stay curious, and remember, you are made of stars, warmed by stars, and forever connected to the cosmic dance of energy that makes life possible. Thank you for being here with me today. I'm grateful for the time we've shared exploring this beautiful story together.